So hi everyone. We'll get started. In the morning session, we've got 5 talks. First of which is going to be Sam de Regt talking about double delight, CRIRES plus insights into the nearest brown dwarf binary. Just a note for all the speakers: just use that mic and stay close to the lectern.
All right, thank you, Sid. Are my slides? Nope, that's the wrong one. Just a second. Displays. Mirror. Yeah. And then full screen. Yeah. All right. Welcome, everybody. Good morning. Today I'll be talking a bit about studying the nearest known brown dwarfs using CRIRES+. I'm Sam de Regt. I'm a second-year PhD student working at the Leiden Observatory, supervised by Injan Snellen. And today I'll be showing some preliminary results. So the nearest brown dwarfs are our nearest neighbors, lumen 16 or WISE-1049, at a distance of only about 2 parsec. And due to their proximity to Earth, we can get extremely high signal-to-noise observations of them. And who doesn't love that? With these high signal-to-noise observations, you can create a sort of benchmark for studying high-mass exoplanets, these directly imaged super Jupiters. For directly imaged planets and brown dwarfs, we are always interested in what sort of spectral types they are, and lumen 16 span the so-called LT transition. And in a column magnitude diagram, this transition can be seen as a sudden shift towards bluer colors. And this rapid change in colors is likely related to the dissipation of clouds in the photospheres of the cooler T-dwarfs. And as these clouds begin to break up, this can leave a patchy cloud egg on the surface of these brown dwarfs, which in turn can lead to photometric variability as these surface features rotate in and out of view. And several studies have documented this variability for lumen 16, with an extremely high considerably high variability detected for lumen 16b, with also a very recent paper actually. Lumen 16b was also the target of a successful Doppler imaging campaign back in 2014, led by Ian Crossfield using the old CRIRES spectrograph. And using high-resolution spectra from the old CRIRES, they were able to track the changes to the line profiles over a full rotation period of lumen 16b. And with that, they were able to infer a brightness map that looks like this, showing the surface inhomogeneities of this brown dwarf. Now, recently, CRIRES got an upgrade to CRIRES+, with a major increase in the wavelength coverage. And we had the opportunity to measure the lumen 16 binary with CRIRES+ as part of the ESO subjob survey. And this is a large program in which we try to distinguish the formation pathways of isolated brown dwarfs and planetary mass companions using chemical and isotopic formation tracers, such as the C/O ratio or the 12:13 carbon isotope ratio. If you want to learn more about the ESO subjob survey and see more results from this, you can check out Dario Gonzalez-Picos' poster up in the hall. So in these K-band observations for lumen 16, we have good coverage of absorption features from water and CO, but we can also see the onset of the methane depression starting at about 2.2 micron. Now, these data might appear a bit noisy due to the way I've plotted it here, but when we zoom in on one of the spectral orders, we can see just how good of a quality these data are. And to make it even more impressive, we got these sort of signal to noises in only 20 minutes of exposure. Yeah, these are very bright. So when we compare the line widths of lumen 16a and 16b, we can already tell that they experience different levels of rotational broadening. And if we try really hard, we can even see that there's a slight Doppler shift in the lines between the two objects due to the orbital motion of these two. Now, to analyze these spectra, we make use of an atmospheric retrieval framework where we couple the nested sampling algorithm by multinest with the Petit-Retrans radius transfer code. And then by parameterizing properties of the atmospheres, we are able to generate model spectra and fit those to our observations, all the while retrieving posterior distributions for set parameters. And part of these parameters are a description of the chemistry of the brown dwarfs, and including that, we find detections. We find confident detections for the following species: 12CO, water, methane, ammonia, H2S, HF, and 13CO. And on top of that, we find some tentative constraints on the oxygen isotopologues of water and CO. Now, these species, these detections can be confirmed by doing a Bayesian evidence comparison or by doing a cross-correlation analysis. However, given the quality of the data, we can actually infer the presence of certain molecules just from their effect on the spectra. So here I'm showing the best fitting model spectrum to Lumen 16b, including all of the molecules that I mentioned before. Then when we leave ammonia out of the spectrum, we can see that it begins to deviate from the observations around certain lines. And this deviation becomes even more apparent for other molecules like 13CO or HF, and including all of these molecules considerably improves the fit. To our knowledge, hydrogen fluoride had not been detected in substellar objects before the subship survey, but since then we have been able to detect it in several of these low mass objects. Now on to the main topic of this talk, which is rotation profiles and surface mapping. So Lumen 16b is of course rotating, which means that certain regions of its surface are blue or redshifted. And combining this velocity map with this limb darkening map, we get an asymmetric broadening of the spectral lines. Now, surface inhomogenities can cause these lines to become asymmetric. These line profiles to become asymmetric. So, for example, if the redshifted hemisphere is cloudier than the blue shifted hemisphere, we would see that the line becomes skewed towards blue shifted wavelengths. And yeah, if a surface inhomogeneity affects both the blue and the redshifted hemispheres equally, this can still lead to a symmetric broadening of the spectral line, just different from a homogeneous surface. And this would be the case for a zonal band, for instance, where we see less contribution from the high velocities at the limbs of the brown dwarf, and thus we see that the line becomes narrower, and narrower compared to the homogeneous surface. Now, it will be difficult to infer these surface features from just a single line profile, but fortunately we observe many hundreds of lines. So when we fit the Lumen 16b spectrum with a homogeneous surface model, we find a solution that looks like this. And to figure out how well this surface model works, we can perform a cross-correlation between the residual spectrum and an unbroadened template. Effectively, this allows us to sum up the residual, sum up hundreds of residual line profiles. And that cross-correlation profile is shown here on the top right, where we see that there's still considerable residual cross-correlation. What we also see is that these features are much broader than the spectral resolution, and they're also different from the primary component. And thus we conclude that these features are genuine and they originate on the surface of Lumen 16b. Now, the question arises, where does this actually come from? What sort of surface features are there? And we just saw that a zonal band can create similar looking residuals compared to a homogeneous surface model. And so we decided to fit for such a zonal band. And we do manage to constrain a band around a darkened band around the equator. And by doing a Bayesian evidence comparison again, we find that this zonal band model is favored at about 20 sigma compared to the homogeneous surface model. And this improvement can also be seen in the reduced cross-correlation residuals. Now, this darkened band was not found in the crossfield analysis back in 2014. And that's because this Doppler imaging technique that was used with the old CRIRES spectrograph is known to be sensitive to, mostly sensitive to rotationally variant features, but the zonal band would not change with rotation, and thus it needs to be inferred directly from the line profiles. And we performed this direct retrieval, but since we only have 20 minutes of data, we cannot create a global brightness map like it was done in the crossfield paper. The decreased line depths at the equator are likely related to the presence of cloud bands around these latitudes, as other work has also been predicting. And with our surface mapping analysis, we find the first spectroscopic evidence for such zonal bands. Now, what you might have noticed is that the cross-correlation profile still shows a persistent asymmetry. And this persistent asymmetry might be related to a spot on the surface of lumen 16b. There are several ways in which the line depths can be altered. I already mentioned that the cloud opacity could create different line depths, but also changes to the temperature profile over the surface or changes to the chemical abundances over the surface can create asymmetries as well. Now, these three processes are, of course, coupled, but we can test whether different molecules have local abundance deviations by cross-correlating with a template that includes only species from one molecule. When we do that for that species-dependent cross-correlation for CO and water, we find that there's not much residual structure left. However, when we do the same for methane, we find that there's that it's remarkably similar to the total cross-correlation signal. However, annoyingly, we have to deal with tellurics here, and we see that this asymmetry lines up with the expected velocity for any tellurics. However, when we do the same telluric removal and cross-correlation on a standard star that was observed just before this target, we do not see the same pattern. So this suggests that our molecular correction for the tellurics works at least reasonably well, but this is still ongoing. Now, if this surface inhomogeneity is, or if this chemical inhomogeneity is really there, it does make some sense that methane will be most significantly affected, because methane is known to be driven out of equilibrium, for example, by vertical mixing. And so three-dimensional atmospheric dynamics might upset the local chemistry and thus create chemically distinct spots, as has also recently been shown in general circulation models. So to sum up, with such high-quality spectra of lumen 16, we are able to suss out the presence of a whole range of molecules in isotopologues, and from just the K-band alone. And through our surface mapping analysis, we find the first spectroscopic evidence for an equatorial cloud band on lumen 16b, and a persistent asymmetry in the cross-correlation profile is suggestive of a chemically distinct spot on the surface of this brown dwarf. Thank you for your attention.
Thank you, Sid. Let me go see my screen. So good morning, everyone. I'm Ben Liu, right now third-year postdoc at NASA Ames. So thanks for the opportunity to share my work with you all today. I'm going to talk about the retrieval of the amazing JWST data of a cold brown dwarf. Before I begin, I would like to acknowledge my collaborators here, including Mike Lai, who is also here, and also other GTO team members. And this work has been published on the Astronomical Journal earlier this year, so feel free to check out because I don't have time to go through all the details here. And since we have from a different background, I would like to give a brief introduction about how brown dwarf have provide a good synergy that bridge between the stellar size and the exoplanet atmospheric size. So brown dwarf typically have a mass of 12 to 70 Jupiter mass, and for our target today, a cold white dwarf, they typically have a temperature of less than 500 Kelvin, and given their low temperature, we expect them to have less than 20 Jupiter mass. So this is one of the coldest objects in the of substellar object that is maybe have a great analog to our Jupiter in our solar system. So in the next few minutes, I think I want to emphasize more about some of the interesting facts and the synergy between brown dwarf to stars and exoplanets. So first, brown dwarfs span a wide range of temperature, gravity, and metallicity, and they are excellent exoplanet analogs, especially for direct image planet, to characterize their atmospheric structure and composition. And because they are easier to observe, we can relatively easy to retrieve their C2 ratio, metallicity, and compare a large sample of brown dwarf, like what Dalasky et al. 2019 show here with HT spectra. And we can, based on this sample, we can compare with the stellar abundance and test whether or not the spread and distribution share similarity or different with the local main sequence stars. And with the high quality data, as Sam shown in the earlier talk today, we can also study the atmospheric homogeneity, dynamics, to study how the brown dwarf flux, color, spectra change with their rotational phase. And since we have many crowds here are studying ultra hot Jupiter and hot Jupiter, I think I would like to point out that there are almost a dozen brown dwarfs are actually orbiting a white dwarf, and they experience strong irradiation. And this kind of brown dwarf, this is the video showing you the HT emission spectra with just 4 HT orbit to study how the spectra change as they between the day and night side of this strongly irradiated brown dwarf. So feel free to check out some of these weird brown dwarf systems. And the target of my talk today is a peculiar white dwarf. So as you point out, you can see in this red arrow here, this white dwarf, WISE1828, is one of the most peculiar white dwarf because it has a significantly red J-4.5 color Spitzer band compared to the rest of the brown dwarf here you show on this plot. And so we expect them to have 5 to 12 Jupiter mass, and with a temperature about 300 to 450 Kelvin. Many people have been struggling in broader community, struggling to come up with different hypotheses to explain the weird color, including binarity, patchy cloud, non-stellar metallicity, C2 ratio, weird TP profile, or non-equivalent chemistry. But none of this can successfully explain all the observed spectra and mid-infrared photometry. This is why we need JWST for this cold white dwarf. So we include this as part of a GTO program in JWST in the cycle 1. So the key question that I want to address in my talk is that what are the atmospheric abundance, C2 ratio, and metallicity of this peculiar white dwarf? And this is the spectra of near infrared that we get from 14 hours of Hubble Space Telescope. And this is what we get from 0.7 hours JWST 395H spectrum. And I plot the y-axis at a log scale because I cannot fit them all in. And otherwise, you won't see the HT spectra here. And all the features you see here are real from the JWST. And to analyze and retrieve this peculiar white dwarf, we use two models. One is a atmospheric retrieval framework developed by Mike that include 33 parameters, including TB profile, clouds, molecular abundance, radial velocity, V-sign, and aero inflation factors. And we also compare the physically self-consistent model of our grid models to cross-check our result as well. And with this fourth model grid, they include temperature, metallicity, C2 ratio, and vertical mixing, which is a proxy to model the non-equivalent chemistry and also V-sign, RV, and aero inflation. So based on this spectra, we can retrieve 6 molecular abundance, and I will show you here what is the all the 6 molecular abundance. So first, you can see the color line here show the methane absorption features, which is shown on the right axis. You can see the blue line. The deeper the blue line go, the stronger the absorption it is. So you can see the strong methane absorption in this cold white dwarf atmosphere. And then we also have CO, CO2, water, ammonia, and hydrogen sulfide. So you can notice that on the right, you can see the precision has become like incredibly good with this high quality JWST spectra. And in fact, you can only constrain the CO, CO2, and H2S with JWST. And you cannot do this with HST spectra. And this is actually the first measurement of H2S abundance in a white dwarf atmosphere. And I would like to point out that we also do not detect phosphine, pH3, that we expect to see in a non-equivalent chemistry atmosphere like WISE-1828. And we do see pH3 in our Jupiter, but we do not see it in a white dwarf, and also not just this, and also in many other brown dwarfs as well. So this has been a huge mystery among brown dwarf community about why the absence of pH3 in the atmosphere. And with this C2O ratio, with this molecular abundance measurement, we can directly constrain the C2O ratio and find them to be roughly consistent with the solar value. And for the metallicity value, we find that the retrieval result and the fourth model grid result are slightly different. I think the retrieval result prefer a high gravity and high metallicity, while the fourth model grid prefer low metallicity and low gravity. We think that this is likely because of the degeneracy between gravity and the metallicity. So with this high precision C2O ratio and metallicity measurement, we can again look at this plot. We find that WISE-1828 is consistent to what we see here with a local main sequence star and also brown dwarf. But you can see that the previous HGT spectra had much larger uncertainty, and with this one we have reached about % level precision with JWST data. And since many of us are using use ground-based high-res spectroscopy, I think I want to point out that I think it's very exciting to see the abundance of H2S, because right now we only have maybe 2 or 3 H2S measurement with ground-based high-res spectroscopy and also JWST. So it'd be great to see have more measurement of sulfur species in substellar and also exoplanet atmosphere. And this also, I would also point out that for JWST, we also have a SO2 in the exoplanet atmosphere. So right now, it's really a cool time to study more about the sulfur chemistry with JWST and ground-based instruments. In addition to molecular species, we also have put the upper limit on the 13 CO abundance with a retrieval result. And we find that the 12 CO to 13 CO is consistent to the solar value. And when we compare our spectra with the fourth model grid, we also do not see any evidence of CH3D. And right now, for this one object, I think this is not just the only isotopological constraint with JWST data. In fact, I think Paul Mullier and also David Brado et al. in last year also reported a nitrogen isotopological measurement for the same target. So we have 2 isotopological constraints for this cold white dwarf. I think many more of these sample or measurement like this will inform us about what can the isotopological measurement tell us about the formation and evolution scenario. And I want to point out that I think, in fact, I think some of the coldest brown dwarf, we also have a tentative, I think we also have a CH3D measurement led by, I think, Melanie Roland from UT Austin. And I think with more isotopic measurement for brown dwarf and exoplanet, I think it'd be cool to understand what can we learn and interpret the formation and evolution scenario. And we need maybe stellar people and physics people, stellar people to tell us about how the nucleosynthesis process can inform about the planet formation as well. So in summary, to answer the question I bring out in the beginning of my talk, we retrieved the abundance of 6 molecular species with retrieval models. And this is the first measurement of hydrogen sulfide in a cold white dwarf atmosphere. And based on this measurement, we can directly constrain the C2 ratio, and the metallicity is more model dependent. And for this diverse crowd here, I think in this conference, I think I encourage us to talk more about, I think, the hydrogen sulfide and what can we do about with these 6 molecular species like carbon, nitrogen, sulfur, and oxygen-bearing species. What can we use this as a tracer to constrain the planet formation scenario? And the missing phosphine also suggests that we have some incomplete understanding about line list or chemistry in cold brown dwarf atmosphere as well. So with that, I will take questions. Thank you.
And next up, we have Allan Denis, who's going to talk to us about characterization of AF Lep at high spectral resolution.
Hi, so hello everybody. So I'm Allan Denis from the Laboratoire d'Astrophysique de Marseille, and I will present you the characterization of AF Lep B at high spectral resolution using the new instrument HiRISE. So maybe you have seen the presentation from Jean Coste on Monday on HiRISE. So now I will present you a detailed analysis of the exoplanet AF Lep B. Okay, don't know why. So first, small characteristics of AF Lep B. So AF Lep B is a late L type companion with a low temperature, and the surface gravity estimated of around 3.7, with a young age. Dynamical mass has been estimated. So AF Lep B is one of the lowest massed exoplanet targeted by direct imaging, which makes it a very interesting target to study. It has a flux ratio of 10 to the -5 between its host star and an angular separation of about 300 milliarcseconds. So it has been discovered in 2023, so very recently. Here you have beautiful images of HoRSEs, where you can see the companion on it. And a recent study from William Balmer, which is submitted, not accepted yet, but has concluded that the orbit of AF Lep is nearly circular. So with HiRISE, we observed AF Lep on November 2023. We did 2 nights of observations with HiRISE. So we, as maybe if you listen the talk of Jean Coste, you know that we need to target the star before targeting the companion with HiRISE. So that's why we did some observations on the star first, with 2-minute integration times on the first day. And we targeted then the companion with 100 minutes on total integration time. We can see here the total integration time. So the conditions were pretty good on the first day, with seeing between around 0.6 arcsecond and a coherence time of about 5 milliseconds. So the total transmission measured during this night was about 4%, which means that we only get 4% of the total photons that are coming to the telescope, which is a major limitation of the instrument, because we have to deal with very low signal in the HiRISE. On HiRISE, we also need to observe backgrounds with the same integration time as the companion. I will explain later why we observe background on HiRISE. On the second night, we observed also we observe a bit longer on both the companion and the star, as we observe the star during 8 minutes and the companion during 140 minutes. And on the second night, the conditions were pretty more unstable, because we are seeing between 0.8 and 1 arcsecond and a coherence time around 5 milliseconds, and the total transmission measure a bit lower than the first night. So we did a custom extraction pipeline of HiRISE. So here you have the raw data. So here you can see the science fiber above, and below you can see some really bright signal, which is coming actually from the adaptive optic guide star fiber, and the backgrounds are used for correcting actually this guide star, because this signal is also included in the background observations. So here you have the total calibrated data with the background, flat and bad pixel map also. We also apply recalibration with TerraRix, where we use polynomial between order 0 and 2, depending on the night, in order to correct for the initial wavelength calibration, which we found to be not optimal in HiRISE. Here you can see some examples of the custom extraction pipeline project. So you have the transmission here. You can see the 4%, almost 4% peak for AF Lep. Here you have the filtered signal in red, and the same thing on the star. So how can we model this data afterwards? So here you have the data of AF Lep, and you need to use models to model the data, right? So you have the model, but in the data you have the terrorix included and also the total transmission of the instrument. So we can multiply the model by what we call the response, which is the estimated transmission of the instrument, so instrumental plus atmospheric response. The problem is that the response includes the transmission of the instrument, but it doesn't include the brightness of the companion, because the model is at a certain flux and the companion is at another flux. So to take into account this brightness, we need to multiply by some component, which we can call the companion, the planetary contribution to the data. And we need to add to the data the star. So the star signal comes from the observation of the star. And for the same reason, we need to multiply the star by stellar contribution. So in final, you can write this model under matrix form. And this phi here contains the stellar contribution and the planetary contribution, whereas the matrix M contains the data of the star and the response multiplied by the sorry, it's a mistake here, but it's a model here and not CS. So to forward model the signal, we used ForMoSA, which is a tool developed in collaboration with Simon Petrus, Paulina Palma-Bifani, and Matthieu Ravet. So ForMoSA is a great tool to do some forward modeling of the signal. We can use different grids. So here I used the XRM grid. You can use different parameters with different prior. So I picked the classical prior, which are uniform priors. And you can also pick your log likelihood function. And also you can custom your own log likelihood function, which allows you for a lot of flexibility in the version. So here I picked this log likelihood function, which actually corresponds to the classical one, where you take the data and you subtract with the models, and you take into account the covariance matrix. So here, phi hat is the linear least square solution to the system here, and sigma 0 is the covariance of the data. So the results of ForMoSA are presented here. So here you have in black the raw data of AF Lep. In blue, you have the estimated stellar model of the signal. In red, you have the full model, but you cannot see here because it is hidden by the stellar model. And you have in brown the companion signal. So here the signal estimated for AF Lep, which is very low, as you can see, and which is actually expected. So if you zoom in, for example, for one of the order, you see here, this signal here. So here you have the data minus the star estimated, and in red you have the companion signal. So what we can do here, because of the because the planet model is broadened with some V sin I, the intrinsic resolution of the planet model is lower than the true resolution of IGRINS, because the effect of the V sin I is to decrease the resolution of your model. So what we can do is we can remove all the features that we can see in the data in the high resolution by applying some smoothing at intrinsic resolution of the data. And when we do that, we find this. So here you have in red still the data minus the star, but smooth at a resolution corresponding to the intrinsic resolution of the data, which is around 23,000. And in red, you have the planet model still. So we can see that it's you have a pretty good match between both signals. I also plotted the planetary contribution and the stellar contribution of the function of the spectral orders. So as I told you earlier, the planetary contribution could be interpreted as the brightness of the planet, whereas the stellar contribution could be interpreted as the brightness of the star. So when we do that, and keeping in mind that the flux ratio between the planet and the star is 10 to the minus 5, we find 10 to the minus 4. So at first, I was very annoyed by this result. But actually, we need to take into account the digital integration time, because we did 20 minutes on the companion and 2 minutes on the star. So when we take into account the digital integration time, we actually find that the CP over CS is around 10 to the minus 5, which is exactly the value expected for AF Lep B, which is a good thing because we are able to retrieve the flux ratio of AF Lep B and its star. So I know that you've seen it a lot this week, but I won't spare you it. So time for cross-correlation function analysis. So here you have the cross-correlation function for the first night with the full model, with some H2O model, and with some CH4 model. So we find detections on the 3 models for the first night. For the second night, although, we find detection for the full and H2O too. But for CH4, unfortunately, we do not find any detection yet. Some atmospheric characterization now. So here you have the corner plot from ForMoSA. So here you have log G, metallicity, C2 ratio, radial velocity, and this and I. Be careful because the radial velocity of ForMoSA is not corrected for the star radial velocity and barycentric correction. So here you see the total radial velocity of the system. When we apply this correction, we find a bit lower radial velocity, as you can see here on this table. So here you have the parameters found on both nights. So they are very consistent except for the metallicity and maybe the C2O, which is a bit lower on the second night. In my opinion, as I saw on different studies, the metallicity for very high resolution data can be very tough to constrain because we have a very narrow wavelength range. So I think it would be very good to make use of both low resolution data and high resolution data in order to be able to retrieve well the metallicity of the data. So AF Lep, to conclude with, AF Lep is the directly imaged exoplanet with the lowest mass of one of the lowest mass, which makes it a very interesting object to study. The detection of AF Lep B on both nights seems confirmed given the results. We have the first direct measurement of projected rotational velocity and radial velocity of AF Lep, and a good thing to do in the future would be to combine low resolution data and high resolution data to better constrain some parameters as metallicity, for example. I leave you with this beautiful horse because this is the. You have some questions?
We have Matthieu Ravet talking about characterization of beta Pictoris B with gravity high res, a multimodal case study with ForMoSA.
Hello.
Well, at first I would like to thank the organizer for letting me present my work today. And so we are going to go back to Pictoris B with the new dataset obtained with the gravity interferometer. And I will also present the work we've been doing to try to combine this spectrum with dataset that exist on this target. So first, Pictoris system, I guess a lot of you already know this system, but just a quick overview, and I really like this sketch. So on the left, you see the, I guess, far-on view of the system with the star on the center and the disk, because this is a very young system. And on the right, if you zoom into the cavity, you can see the two known exoplanets that have been detected. So Pictoris B, the first one, and the farthest one, and then Pictoris C on the center. So today we are going to go back to Pictoris B, which is the one we have the most dataset on. And actually, this is one of the reasons we choose this target for our study. So, like I said, very young system, only a few million years, and a very bright exoplanet. So I guess kind of easy to get data on it. But the main reason is, like I said, we have a lot of spectroscopic and also photometric data on this target. And so if you want to try, I guess, to combine, like Allan mentioned, high resolution, low resolution, different wavelength coverage, this is the perfect target to do it. And so, well, like you imagine the end goal is to try to constrain and maybe refine the formation scenarios possible for those type of objects. So first, the gravity spectrum. So Beta B was already observed at low resolution with the gravity interferometer, so at a resolution of 500. But recently we obtained four new nights with the high resolution mode of the instrument. So high resolution for you is maybe a bit too low. This is 4,000. But nonetheless, the spectra is very nice. So we have both the continuum information. So as you can see, the shape of the K-band with the two H2 absorption band at the beginning and the end. But for example, we also see a lot of molecular information. So the CO absorption near 2.3 micron. So here also at the top of the screen, you can see the covariance matrix, which can be estimated empirically with the interferometric dataset. And you can see that, so this covariance basically represents your error and both your correlation, spectral correlation on your data. And so you can see that, for example, at the end and the beginning of the K-band, you have quite a lot of correlated noise, and I will go back to it in a few moments. So to work on this data, we also used ForMoSA. So I won't present too much the code, but the idea is for one modeling. So you have a set of spectroscopic and or photometric data that you want to compare with grids of models that are usually involving physical and chemical constraints on your atmospheres. And so we choose to compare the spectrum first with 4 different grids of atmospheric models, which encompass different assumptions on your atmospheres. And here I'm showing the fits. So on the top you have ExoREM and Atmo, MITI-SETTLE and Sonora. So usually they encompass the physical contribution of clouds in the atmosphere, but for example Atmo is the only one who does not, and instead try to replicate the effect of clouds in the atmosphere by involving fingering convection, which is triggered by non-equilibrium chemistry in the atmospheres. And unfortunately, this is the model that fits the worst. If you look into the posteriors on the left here, practically all parameters are at the grid border and are highly unphysical. And if you have a good eye, you can almost see at the top of the K-band here, the fit is slightly worse, but it's difficult to see. But nonetheless, most of the models agree pretty well on the retrieve parameters, especially the effective temperature. Both converge toward around 1600 kelvins, which is comparable to what is predicted for the evolutionary models, so around 1700 Kelvin. So 100 Kelvin difference is reasonable and is probably more representative of the real error you make on this parameter when you use for modeling. But then it gets a bit more difficult. If you look, for example, at the log G, this time we have a lot more variation, although still around the value predicted. But I guess what interests you the most are the chemical abundance and the molecular ratio. And so for the grids that explored the carbon to oxygen and or the metallicity, what we find is that, for example, for the CO, we obtain a solar value, both for ExoREM and for MITI-SETTLE, and the two grids that did not explore this parameter are fixed with a solar value. which is kind of surprising because the previous study, especially on the gravity data, found a subsolar value, and also the recent retrieval with the CRIRES data plus, CRIRES plus data. So yeah, this begs the question on how much can we use this ratio to really probe the formation and evolution of planetary systems. And also for the metallicity, as you can see, it's even harder. So we see a trend for the two models that do converge towards a very high metallicity, but again, very hard with only one spectrum actually. So we also try to explore the isotopic ratio for this target, although it is complicated because the resolution is quite low. So here I'm showing the end of the K-band on the right, a zoom-in version where you can see, well, kind of see the model with 13 CO and the one without. So we use ExoM, which is a custom version of ExoM that encompasses 13 CO variations. And we are able to obtain an upper limit on the ratio 12 CO over 13 CO of around 14.5, which is extremely low. So I give a comparison with the solar value, the ISM value around beta peak B, and a very enriched brown dwarf. As you can see, this suggests that you could have a very enriched atmosphere in 13 CO. This is very dubious, and that's why we wanted to try if we really detect 13 CO in the atmosphere. So we proceed to do a cross correlation similar to what was already done in papers such as Yapen Zheng paper on YSMB actually. And so here again, the story is more complicated because there seem to have a lot of tellurics, residual tellurics actually, at the end of the K-band. So although you see a peak at the center of 0 kilometers per second, it's kind of hard to conclude on exactly how strong the detection here is. So maybe we detect 13 CO, maybe not. This has to be checked again. So that's it for for gravity. But the end goal of the work is to try to combine this new spectrum with the existing one. And so what we did, is to create a new framework in ForMoSA to efficiently combine different data sets. Because, well, the first idea could be to have like one big data and one big model, and you put in your favorite Bayesian estimator, and tada, you have a nice posteriors. But it's more complicated than that because you have a lot of difference between, for example, high resolution and low resolution spectroscopy. And so the idea we had was to basically cut your model in subgrids. So you have a general model here with some parameters, theta, and we'll cut in a grid 1, grid 2, grid n for each data set. And doing that allows you to basically extract and adapt your grid for the needs of your data. So for example, if you need a grid at high resolution with a certain wavelength range without continuum, then you could have it. For example, if this is CRIRES, you want a special subgrids. Then you can compute your likelihood, your Bayesian estimator, and at this point you can add extra parameters, which I'll call here theta prime 1 and 2 and 3. So these extra parameters are parameters that you can define separately. For example, the radial velocity, if you want to fit different epochs, or for example the burning. And then at the end you merge everything. So here we made the assumption that your datasets are independent because we directly sum the log likelihoods. This is debatable, but it works for now as a first approximation. And so if you do that on the beta Pictoris existing dataset without CRIRES for now, this looks like that. So in gray you have a model, ExoM model, and in shade of color you have the different dataset that exist on gravity. And so it looks nice, but we're starting to see some issues. For example, well, it's not very clear, but usually the dataset that have the more ports tends to drive the fits. And for example, you can see that the residual for the low resolution datasets are a bit more variable. So I won't go into detail on the posteriors, but the idea here and the key point we wanted to make is that you need to have a coverage sufficient enough to really probe how well the quantity of your different posteriors, especially the molecular abundance. So the idea here of the plot is basically shading. We add iteratively each dataset onto the fit, and you can see that the posterior is shifted both in the center and in the shape overall. So this is maybe actually more representative again of the real error you are making on your fits. And so recently, this is ongoing work. We've been adding the 2 new CRIRES datasets that have been taken on the planet, beta Pictoris B. So both in K-band and M-band by Rick Hollenman and also Luke Parker. So I work in great collaboration with Allan Denis on this part, and we try to encompass the reduction of the dataset that is used at high resolution, sorry, in ForMoSA. And we are managing to get the first fits encompassing both medium, low resolution, and high resolution with CRIRES in K-band. So this is still very preliminary, and I guess the corner plots are going to look a bit more like retrieval corner plots. But yeah, it looks very nice. We are able to retrieve the velocity, the vis and I, and again, you can see the problem. High resolution is driving the poster. So we might need to go and find a way, maybe with scaling or weighting factors in the likelihoods. And so I will just end with the very, very preliminary work on the M-band data, where we are starting to see some issues, mainly related to ForMoSA. Like I said, the weighting factors I already talked about, but also how well we estimate the continuum, for example, and the resolution when we decrease it for the grids and stuff like that. So I will leave you there with the key points of my talk. Quite a lot of things actually to say, but mainly gravity fits well on its own, and now we are trying to add new data sets. Thank you very much.
Combining high-resolution spectroscopy and photometry to characterize a dayside atmosphere of WASP 178b.
Okay. Can you hear me actually? Okay, perfect. So, well, first of all, thank you very much for having me. I'm David Cont. I'm a fellow at the Origins Excellence Cluster in Munich. Currently, my research is embedded in the Munich Exoplanet chair, and I'm also a member of the CRIRES Plus Consortium. And that's actually also the reason why I'm here today to speak about the Altair Jupiter WASP-178b. This is a paper which has recently been accepted for publication and which was carried out in this collaboration, which basically consists of all these names that you can see up here. So the Altair Jupiter WASP-178b is actually, I think, an Altair Jupiter has been a bit overlooked with respect to other objects. So if you look at the left-hand side to the planetary parameters, you can actually see that this planet has a rather high dayside temperature that exceeds 2,500 Kelvin. We have a scale height which is also considerable, so this is also a good target for atmospheric transmission spectroscopy studies. We'll later see a talk from the ESPESO consortium on that. And also the V and the K-band magnitudes are below 9, so this is a very good object which is recently not deeply investigated, but which actually could be a rather nice benchmark Altair Jupiter for the future. So due to the fact that this planet kind of was promising, we took our CRIRES Plus and performed some observations of the planetary dayside in the K-band between 2.5 and 1.9 and 2.5 microns. And we actually, of course, when we consider the dayside, we are investigating a planet very close to secondary eclipse. In our case, we actually went for the observations immediately after the secondary eclipse. So I don't think that I have to explain too much about the cross-correlation method. Already Jens Hoymakers did this the first day of this conference. So basically, we investigated several chemical species. We found the signature of 2 molecular species, and these are the CO and the water. On the left-hand side, you can see the Petit transmodel spectra used for cross-correlation. In the middle panels, you can see the cross-correlation function maps. And you can actually see for the CO, we have a strong detection. We actually can really see the stripe as it evolves over the different orbital phases in the radial velocity space. For the H-TOW, this is a molecule which is a bit more unstable with respect to the CO, to thermal dissociation. So therefore, we have also the spectral lines, which are a bit weaker. But tentatively, I think you can see here a stripe, how this also evolves as a function of time. And in the right panels, you can see the signal-to-noise detection maps, where you basically see that, well, the CO, due to the low amount of thermal dissociation, has a strong signature with a signal-to-noise of 9, whereas the water is a bit weaker, around 4.5, depends on the cis-rim iteration. So I think a few years ago, probably, this would have been already enough for doing a nice publication. Nowadays, let's say, fortunately, a little bit more is required. And therefore, our next step, we went for an atmospheric retrieval by putting together the signature of the 2 chemical species in a combined signal and investigating that. So in our retrieval framework, as all the retrievals, we basically compare the observed spectra, which is this matrix on the left-hand side, already cleaned for the telluric and the stellar lines. We compare this quantity, denoted as Rij, with the parametrized model spectrum. This is done by means of this well-known log likelihood function. We actually have this quadratic term here, and this quadratic term is minimized when the 2 quantities resemble each other the most possible way. So when this term is minimized, the log likelihood is maximized, and then we use a Markov chain Monte Carlo sampling to basically sample the whole orbital parameter space. And this results then, of course, in the posterior distribution. So I'm not showing here the whole corner plot because probably it's a bit boring and overwhelming with all the parameters. So actually, these are the most important parameters of our retrieval. We find a inverted temperature pressure profile. The temperature pressure profile is parameterized by this 2 points TP profile, where we actually assume an isothermal pattern in the lower and the upper part of the atmosphere and a linear pattern in log space in between the 2. We also have some kind of not too good constraints on the atmospheric chemistry. So in our case, we're assuming equilibrium chemistry. Then it is enough to assume only these 2 parameters, the metallicity and the CTO ratio as the free parameters. But as you can see, high resolution spectroscopy actually just yields rather weak constraints on the metallicity and also on the CTO ratio. Here basically we just get an upper limit. We'll solve for this in a few steps, in a few slides. Then we have an additional term, which is the axis line broadening. So in the radiative transfer calculations, we already include the thermal and pressure broadening, but broadening due to dynamics in a planetary atmosphere in that modeling step is not considered. And therefore, we kind of employ a broadening kernel that assumes solid body rotation. In this case, we get an axis line broadening, which is rather considerable. So I think it's exaggerated to say that we detect strong atmospheric winds around the equator, but this clearly hints towards either winds, jet streams, or also some turbulent motion in the planetary atmosphere. Well, and finally in pink, these are these two velocity parameters that you already know quite well, the Kp and the Vcis. So a first comment on the posteriors is that, first of all, high-resolution spectroscopy apparently seems to be enough to constrain Kp, Vcis, and the equatorial velocity, the equatorial rotation velocity of the solid body quite well. This is, I think, no big news because, I mean, we know we have high-resolution spectroscopy. The spectral lines are resolved. Also, the shapes of the spectral lines should be resolved. So I think this is no big news, actually. If we look at the temperature pressure profile parameters, highlighted here in blue, especially the temperatures, here we can already comment a bit more on this. So we have especially the temperature T1, which parameterizes the upper end of the thermal inversion layer, which is actually not well constrained. This has nothing to do, from my understanding, with the methodology of high spectral resolution that we're using. It's simply the case that going upwards in the atmosphere, the molecules dissociate, and therefore we have actually that no signal is coming from that region, and it's difficult to get constraints on that. However, this should be different for T2. T2 parameterizes the lower part of the planetary atmosphere, and actually here we expect a signature of CO and H2O, which should be considerable, and therefore it's kind of, well, not so trivial to understand why this is actually not being constrained that well. So here the reason is that we have this, I would say, a rather methodological issue. So in principle, in the raw data, the information is still available, but when we are then going for using SysRAM or principal component analysis, what we do is that we basically remove with the systematics also the continuum level. The continuum level encodes the temperature at the bottom of the atmosphere, and therefore also this constraint here is kind of washed out and becomes broader. And this has then as a consequence the fact that also the chemistry, especially in our case the C-to-O ratio, which strongly depends on the temperature pressure profile, is also then in that case not constrained anymore that well. So now to sum up what I've said, actually this is the best fit high resolution spectroscopy retrieval we get. And we said that the spectral line position, the spectral line shape and strength, this is something we should trust from the high resolution spectroscopy. But the spectral continuum level, this red baseline, is something that we should not be that sure about. So it could be also moved up or down. This is something that is not well determined. So how can we solve this issue? This issue can be solved by using space-based data. In our case, we are fortunate enough that there was already this TESS and KOPS data published. So we kind of use these data points in addition, which now measure absolute fluxes and not relative fluxes as in high resolution spectroscopy. And one can go basically for doing again the same thing. So including an additional log likelihood term into our retrieval by comparing the data points from space, which is denoted by R, with a model spectrum integrated over the band passes of instruments, which is denoted by this delta here. And again, we can run the Markov chain Monte Carlo now on the combined log likelihood, and you can get better constraints. And in addition, by using the spectral data from the space, we can actually see that the model includes an emission term, but also includes a reflection term, having therefore also an additional parameter which characterizes also the reflection properties. This is basically the geometric albedo that we include here also. So by using this data, we are actually passing from this situation here to this situation where still we don't get bound constraints. This is a bit a pity, but we only cover now half of the parameter space, so really see that the temperature of the planetary atmosphere at the bottom is significantly lower. The chemistry is now getting also better constrained, and this is kind of also reflected now in the best fit model spectrum of the combined retrieval that you can see in blue here now. So as said before, the line shape, strength, and broadening only slightly change, or almost don't change. But we see that it's shifted down in order to match the tests and the Cheops data points. So basically, the main takeaways of this talk are, in addition to our characterization of WASP 178b's atmosphere, which has actually not been characterized yet, and which I encourage everybody to investigate more, is that actually we find that high-resolution spectroscopy alone is enough to constrain the line profiles and the velocity parameters, but that for determining the thermal and chemical properties, we actually have need for adding space photometric data or low resolution spectroscopy data from the space to get the tighter constraints on these parameters. And yeah, I'm already a bit too fast today, apparently. But with this, I'm already at the end of the presentation. So actually, I have to say, very nice that everybody brings the horses here. I'm more a cat person. So I brought a cat today. And if you want to check out the recent accepted paper, just go and check out the QR code here. And with this, I thank you for your attention. Thank you very much.
you start with this. If we get the French accent.
This session with Gabriel Marleau talking about accreting hot Jupiters.
Thank you very much. So I'm actually Simon Ringqvist, as you can maybe tell or not tell. So he was supposed to give this talk, but unfortunately had to cancel a bit at the last minute. So I came, and I'm here only for today, but it's a pleasure to talk to anyone. So I want to present the results of our entropy collaboration on actually accreting not hot Jupiters, but super Jupiters, but it is a hot topic, so the hot was appropriate. And this is a collaboration. You'll see the pictures of the people later on, looking at super Jupiters, which are accreting at high resolution, but maybe in the context of this room, high resolution is sort of low resolution, but okay, let's see. So there have been searches, of course, for accreting companions. The most famous example is BDS-70 system, BNC, which you see there, which was observed with MUSE. And these companions span actually a range of ages, so a few megayears, as you would expect, but they're actually quite old accretors too, up to 45 megayears. And they're just two names as examples. And they have different architectures in terms of separation from the star, orbital characteristics, and stellar mass, and so on, so the primary. And they've been detected at H alpha, H beta, Paschen beta, also some metal lines. More rare is bracket gamma, for instance, and there are other lines too. And as you can imagine, there's maybe not only one single accretion mechanism explaining all of these objects. And so we want to characterize this in a bit more detail. And we're really just at the beginning. This is 2019. It's only 5 years ago. And we don't know so many accretors yet, sort of unfortunately, but yeah. And the lines can be used, of course, so as I mentioned, H alpha, H beta with these different instruments, also other lines. with upcoming instruments too, which are in preparation. Ristretto is one example, or VisX, which is working at H-alpha. And what we need to do is to study the line in great detail, as much detail as possible, and also look at the time dependence, because unfortunately, or fortunately, these objects also seem to be time variable, which can tell us something about the accretion processes and their physical characteristics. So just to show a bit of an example, or to say this in a bit more detail, the line profiles are related, of course, to the accretion rate. So there's the classical scaling from 20 years ago between the line width at H-alpha, which apparently is independent of extinction. This is for stars, but it can sort of extrapolate towards planets, and hope this holds a bit. Actually, the density and the velocity of the infalling material onto these objects will also shape the line, so will determine the line shape. And the accretion mechanism itself, so whether it's a magnetospheric accretion scenario as for stars, or whether you're talking about only sort of pure shock event where the gas is falling from the heliosphere onto the planet but without any magnetic fields, this is also conceivable. And here's just one example of the models that have been developed by the Hartmann group for T-Tauri stars, now applied to planets by Tanabou Baudet. And you see as a function of phase, a rotation phase of the object, you get a very different or slightly different line profile depending on how much material is between the observer and the emitting region. So studying this can tell us something about the accretion geometry and the accretion physics at all, actually, for these objects. So what is the entropy survey? So it stands for the Exoplanet Accretion Monitoring Spectroscopy Spectroscopic Survey. So picking out the right letters, you can make out this cool word. This is Michael's work. So the PI is Michael Bonnefoy, here at Grenoble, and there's Catherine Ducados, PhD student Dorian Demas, and Jérôme Bouvier is also there, Yuko Oyama in China, originally from Japan, of course, but working in China, Cici and these other people, and also want to highlight Simon Ringqvist, also used to be named Eriksson. It's a Swedish thing, apparently, to take one's wife's name. And Gayatri, who successfully defended just a few years ago. And there's Judith, and there's me in Germany. And so this is actually, so we started doing this some time ago. We had a few nights, some hours. And now recently an approved large program at the LT, UVES, 165 hours, which I'm a theoretician, but I think 165 hours sounds like a large number. Okay, somebody's nodding. Good, thank you. And so this is just an example of one object we've been observing. So I'm saying we, but of course the work is done by the PhD students. So these three in red, sort of former PhD students, are still PhD students. And you see some variability, within the night and between the nights. These are just 4 nights shown quickly. Okay, so let's look at one example, one object in particular, Delarm 1AB. So it's a companion about 13 Jupiter masses. The mass is not too uncertain. 45 megayears old, so this is quite old compared to what you would classically expect for accretion. It's widely separated, 84 AU, from its primary, a binary. And you see the whole Balmer series, helium lines, and also actually some disk extinction, excess emissions coming from JWST data. And if you look at the spectrum, this is with Muse at an extremely low resolution. This is almost a broadband filter of 2,500, right? And you see, so the H beta, and then bam, this H alpha line. And we've observed it now with UVES. So we had 11 visits over 3 months, probing a range of timescales, minutes, hours, days, weeks, and months, actually, resolution 50,000. And this is how the slit was positioned. So the companion is here, very easy to find thanks to the white arrow. Okay, this is a joke. So if you look at the UVES data, it looks like this. This is H beta. So this is one part of the data, H alpha. And actually, this is the primary here. Let me get the pointing right. This is the primary, and you see this fainter trace, which is a companion. And turns out there's a bit of leakage of the primary onto the companion, but we were able to decompose this, and it's okay. I can give details if people are interested. And what you see, so you look at the spectrum of this 13 Jupiter mass planet, right? This is not a T-Tauri star, it's a low mass object. So what you have here, all these hydrogen lines, and you have here actually a heated UV excess, just as for stars, which is presumably coming from a shock. So this may be this picture as in the stellar case. And we see also metal lines, so maybe iron, some helium lamps, definitely. And the question is, of course, what is the physical origin of these different lines? Where are they coming from in the system? So this is work in preparation by Dorian Demas, who's frantically finishing his, writing his PhD thesis, which is, of course, a big effort. So let's talk a bit about the line behaviors. The H-alpha line, very interestingly, this is this one, so H-alpha, or H3, is actually very asymmetrical. And these are different nights, different epochs within the nights and different nights. And if you look at the other lines, so H-beta, gamma, and the mean of the lines, then they're much more symmetrical than the H-alpha. So I'm just describing the data. We don't have much interpretation yet in terms of understanding the models. And all the lines actually show a blue tail. So if you look at the blue side of the line, you see that it's quite higher than the red side on 3 consecutive nights in October 2022, which could be maybe due to a flare. So this is one possibility. And if you look at the helium line, so this is actually a helium doublet, so it's not asymmetrical, it's just 2 different lines but a bit blended. They show variations in the flux only, but not in the shape, so different from the H-alpha. Okay, if we look at metal lines, so I'll just mention the calcium 1 lines. We see several lines which share the same upper energy level, so one could study this to get some information about the emitting region. Hasn't been done yet, but could be done. And we can look also at the iron 1 and magnesium 1 lines. So this is just one small section of the spectrum. So the 0 point in velocity is just at this line, just sort of for reference. You see these different iron lines and magnesium, and actually they appear only during the outburst. The red line is during sort of an outburst epoch, whereas the orange at the back is the quiescent epochs, actually an average of several epochs, I think. And this behavior, so seeing these lines appearing only during outbursts, is consistent with the behavior seen at T-Taurus stars. So this is also very exciting, I think. Now we can decompose the line profiles. So if you look at the H-alpha, beta, gamma, delta lines at all epochs, actually turns out they can be described as being made up of 2 components with the same shapes. So these across the epochs, the components remain the shape, but their relative normalizations vary. So this is, so you see the different epochs here, and you see the decomposition, and the residuals around 5 to 10%. So it's not perfect, but it's actually a very good match. And this is sort of an overview of the profiles. And the blue component can be described like this. So there's a correlation between the blue components at the different epochs between the H-alpha, beta, gamma, delta lines, and it correlates with the UV axis, which also varies. There's also correlation with the helium 1 lines, and this is actually the main cause of the variability of the whole profile. And if you look at the green component, it doesn't correlate that much with the UV excess and the helium 1. It's less variable, so that's a more stable part, and it's also the dominant component of the line. So what the physical interpretation is not clear, so we took sort of one step forward, but it's not the final story yet. We look at pure shock accretion models, which otherwise work well for other objects in describing the line ratios, for instance, but they don't really reproduce the line shape quite well. If we look at magnetospheric accretion models, they have a better fit of the line. It's not perfect, but they don't get the line ratios quite right, but at least the line shape is better. So these are these 2 components, the green and the blue fit separately. So you see the wings are not fit very well, but actually the core of the line is. So between the red lines, the fit is quite good. And it's this kind of picture. So the blue being the blue component and the green one. And it's actually sort of 2 different magnetic spheres with very different properties. So, I mean, you see it graphically, right? This is sort of this wide magnetosphere with a 2 Jupiter radius width, and this is very narrow. This is sort of a higher inclination than this one. So, one possibility could be that actually this object is a binary, so it could be accretion onto 2 different magnetic spheres at the same time, onto 2 objects. Could be. We have time granted to look into this with CRIRES+. It doesn't have to be. Could also be some kind of complex geometry of the funnels. That remains a bit of an open question. Also, of course, explaining the line wings. We don't know what this could be. This is a work in preparation. And I just want to flash quickly a few targets. So I won't reveal the names. There's some Gaia name. But for some, this is a paper submitted, and the first referee report was very good. It's not too much work. You can decompose this line, so H-alpha, for instance, into 3 different components, which can be interpreted in a magnetospheric accretion framework. And this other object has a different variability and cannot be decomposed at all into this blue and this green component as for the alarm 1. So these different objects show different behaviors. and stay tuned for upcoming work. So in summary, I've talked mainly about this one system, DeLorme 1ABB, in the eyes of UVS, and we see different helium and hydrogen lines and also UV excess. Metallic lines appear at outbursts, which is reminiscent or the same situation as for Pictoris stars. And the Balmer lines actually can be described as a sum of two components of stable shapes but varying normalizations. And this could be explained by some kind of two magnetosphere geometry, but what the real physical picture is a bit open still. And we have this entropy survey on VLT UVS led by Michael with many different objects with different separations and masses and so on, and we want to try to understand this a bit more detail. And the students are led by Dorian and Gayatri, and they're looking for postdocs, so if you're interested, please talk to us. I put my email address here because it's short and convenient, but you can talk to Michael Bonfoy, to anyone. And with this, I would like, because it's a sort of French-Swedish collaboration mostly, I would like to say merci and tack.
All right, that should work. Okay, hi everyone, I'm Luc Bazinet. I'm a master's student at the University of Montreal, Université de Montréal, and I will be presenting a paper that was published actually a few months ago, which is called Subsolar Metallicity on the Ultra Short Period Planet HIP 65AB. So I'm not sure if you all know what HIP65AB is, or what kind of planet it is, so I'll try to summarize it a bit. So it's a hot Jupiter, obviously, and it has an orbit of a bit less than 1 day around its K star. Its equilibrium temperature is about 1400 Kelvin, and it has a radius around 2 Jupiter radii. And you may notice that I put some uncertainties on the radius, even though usually I don't do that, and it's because they're quite huge. And if we look at the diagram on the right, you can see that this is a 2-scale diagram of our point of view of the system. So when it transits, when it comes right here, you can see that it has, it only partly covers the planet. So it's a grazing transit, as we call them. And because of that, it's really hard to get the radius, and that explains the plus or minus 0.5 Jupiter radii that we have here. And also, its mass is about 3.2 Jupiter masses. And I'm not sure if you're aware of the scale of these values. So I put the Jupiter masses and Jupiter radii. So I put them in the more natural unit, HoRSEs. So HIP65 is about 90 million HoRSEs high, and about in the order of 10 to the 25 horse masses. More than 2 horses, you're right. So let's go back to real science. And this planet has the highest ESM ever in the infrared wavelength. So the ESM is the eclipse spectroscopy metric, and it is a measure of how good a planet is in emission or eclipse spectroscopy. So you can see on the plot on the right that we have x-axis as the radius of the planets, and y-axis is the ESM at 2.2 microns. And HIP65 towers all over all other planets, even better than the 2 HD planets that we all hear of. And this is mainly caused by its really big radius and the radius ratios between its star. So because of that, it's a favorable target for emission spectroscopy. So there was a proposal, and it got accepted, and I was tasked to look at the data of HIP65AB. So this is the data that I got. So it was from the post-eclipse phases of HIP65AB. So what we also call the western dayside, a 3.5-hour observation taken with IGRINS, and it for context, IGRINS has a resolution of about 45,000, and it covers the H and K bands, which are really good for carbon and oxygen-bearing species such as water, CO, and others. So I'll skip all the reduction part because we've been talking about that all week, and go straight to the results. So here are the KPIC maps for water and CO, and as you can see, there is some kind of detection here. About 3 or 4 SNR, which isn't that strong, but it's still good enough that we kind of declare detection here. And these are the first detection of CO and water on HIP65AB. Actually, what I'm presenting here is the first atmospheric analysis of HIP65AB. And this is predicted by models. We all know that water and CO must be in some kind of high amount in these atmosphere of hot Jupiter, so there's no really surprise here. So with that, we'll try to do the retrievals next. So I'll just go straight to the results again. And here are the posteriors of the molecular abundances in the atmosphere. And that's the orange lines. And the vertical lines are just model predictions from chemical equilibrium for 2 models. So one is a solar C2O, and the other one is a C2O of 1. And you can see that for the top 2 panels are water and CO. They are well constrained, which is what we expect from the detection on the KPIC. And we also included other oxygen or carbon-bearing molecules that are in appreciable amount in the atmosphere. And these are we all found upper limits for these species just because we can't really detect them with enough significance. I want to point your attention toward one panel, the 4th panel in reading orders. It's SIO. And this, you can see that it goes quite high, the posterior. The retrieval favors 10% SIO in the atmosphere, which is unreasonably high. And this is mainly because we don't have major lines of SIO in the IGRINS wavelength, which is unfortunate. Also, we retrieve the temperature profile. So in orange here is the temperature profile we retrieve, with the black dots being the pressures that were fitted. So we fit 12 points in the atmosphere, and we tried to fit it individually. However, we have some kind of what we call a smoothing parameter that prevents the temperature profile to do kinks or being like a zigzaggy profile. And we can see that also the red and blue lines are what we call the contribution functions. So these are like where these molecules probe in the atmosphere. So we can see that CO probes a bit higher while H2O a bit lower. And in this region, we see a non-inverted temperature profile, which is what we expect from these kinds of planets. The teal line here is the condensation curve of MJSIO3. And you can see that the temperature goes lower than that. So if there were maybe MJSIO3 in the atmosphere, we could expect it to be condensed. However, I won't show it here, but we also fitted the cloud top pressure, and we see that cloud tops don't really affect our spectrum. So we concluded that clouds aren't really prominent in, or at least where we probe in the atmosphere. So now let's go into chemical, elemental ratios. So first I calculated the C2O ratio with just taking data from a retrieval, and we see that there is a really big lower bound, and this is caused by SIO, like I said earlier, that is pretty much unbounded. So we calculated another C2O ratio where we excluded high SIO scenarios, and we see that the two values are really like in the supersolar part, but also consistent with solar. So it's really hard to really point that out. The two others are like metallicity proxies, so with carbon and oxygen. And we see that they are both negative, meaning that it is a subsolar metallicity. And just to have some kind of consistency, we also do it with chemical equilibrium instead of a free retrieval. And we see that the C2O and the metallicity are really close to the free retrieval, which is good for consistency. So this can tell us a bit more about where HIP65AB was formed. So there's actually two scenarios, two main possibilities for the formation scenarios. The first one is if we were able to get all the oxygen in the atmosphere, this would point toward a formation that is beyond the H2O and CO2 snow line, but we know that HIP65AB is not there presently. It's really close to its star. So it would be followed by some kind of migration inward to its current position, and most probably in a disk-free scenario, so where the disk is dissolved. The other possibility is maybe if we retrieve oxygen is not representative of the oxygen content, so we're missing some oxygen somewhere. This can be maybe because the SIO is higher than we thought, or maybe it's condensed in some kind of oxygen-bearing molecule deep in the atmosphere, or maybe in the night side. So this would point towards some kind of formation inward of the H2O snow line, so not a lot of migration. And also it could point toward a formation through gravitational instability instead of the core accretion that we always think of. So lastly, we also compared with our data, our results with the hot Jupiter WASP-77AB. So on the left, we see that these are all posteriors of water, CO, and also the C2O ratio. And I want to point out, firstly, the green and purple posteriors. So these are both WASP-77AB results taken from IGRINS data from Mike Lyon et al. And the green line is from the work from Mike Lyon, while the purple line, yes, is from the same data but passed through our reduction and retrieval pipeline. And we can see that they are virtually the same, especially for H2O. And that's just more of a sanity check that our pipeline is really consistent, at least for that planet. So now we're comparing to the orange line, which is the posterior of HIP65AB. We see that we have a depleted H2O, while the CO is really spot on for compared to WASP-77AB. And something to note is that WASP-77AB is a bit harder than HIP65AB. So a possible explanation is that maybe there's some kind of oxygen-bearing molecule that is condensed in HIP65AB that is not condensed in WASP-77AB, which may take away oxygen and prevent water from forming here. This is an avenue that I feel like it's worth exploring a bit, like comparing hot Jupiters like this, but yeah. So this is like some kind of first impression on that. Okay, so here are just my conclusions. So we first detected H2O and CO on the hot Jupiter HIP 65b using cross-correlation. We find a subsolar metallicity. However, the C2O ratio is a bit more uncertain because of SIO, so it could be more in the solar or subsolar, supersolar, sorry. And also formation scenario includes some formation beyond the major snow lines, followed by some kind of migration, or in situ formation by gravitational instability. And here's the QR code that leads directly to the paper. I encourage you to look at it if you want more information. Thank you.
We will have Luc Finnerty talking to us about the atmospheres of ultra-hot Jupiters.
Okay. There we go. So, hi everyone. My name is Luc Finnerty. I am a 5th and final year graduate student at UCLA in Mike Fitzgerald's group. And today I'm going to be talking about part of our ongoing KPIC survey of hot Jupiters. So KPIC's been mentioned a few times before at the conference, but I wanted to just go over it again. The idea is to feed NearSpec, the Keck high-resolution infrared spectrograph, using a single-mode fiber so that we get diffraction-limited high-resolution spectroscopy, originally intended to do directly image companions, where you want that high spatial resolution to reject starlight. The advantage is that this also gives you a really stable backend, which is really helpful if you want to do high-resolution cross-correlation, which with seeing limited NearSpec is a bit of a challenge if there's anyone in here who has tried that. Beginning in 2025A, KPIC is available as a facility instrument for K-band observations, but we can also observe in the J, H, and L band. So if you're interested in that, talk to me and we can try and make that happen. So we have started a large survey trying to get 20 to 30 hot Jupiter atmospheres with KPIC. The survey summary plot is here. So far, we have about 12 detections. We have another 2 or 3 where we're trying to pull stuff out. The telluric correction is a bit challenging for those. And we have another 11 targets scheduled for the remainder of this semester and next semester to round out the survey. We'll see whether the weather starts cooperating a little more than it has been. And this survey spans kind of 2 decades in both mass and insolation, and the goal is to get at sort of the population level, what is the distribution of things like the C to O ratio and the atmospheric metallicity that we think are potentially important tracers for planet formation and migration. So I'm today just going to focus on these 6 ultra-hot Jupiters that we've detected so far. And those are WASP 189b, Mascara 1b, TOI 1518b, Kelt 20b, WASP 33b, and Kelt 9b. And all of these we have detections with thermally inverted carbon monoxide models, which is good, what we expect. We expect to see strong inversions and carbon monoxide in ultra-hot Jupiters. I don't have time to talk in detail about 6 planets, so I'm going to focus mostly on Kelt 20b and Kelt 9b, and then come back to what we're seeing for all 6 of these as a whole towards the end. So other people have talked about atmospheric retrievals before, so I won't spend too much time here. But people have talked about both free retrievals, right, where you fix the abundances with altitude. And the problem for ultra-hot Jupiters is that there's dissociation, so this will bias the abundances you achieve. You could alternatively do an equilibrium retrieval, right, where you have some equilibrium chemistry model, and that handles the dissociation for you. That's nice in that it eliminates free parameters, but it does add model assumptions, right? And you'll miss photochemistry if that's happening. So what we're going with is a free plus dissociation approach where we treat the dissociation as a free parameter. This is great because it's flexible, but it increases the number of free parameters, which can cause problems, which I will get to. So this is what we get for Kelt 20b. This is just a subset of our corner plot. We have constraints on water, carbon monoxide. The OH and acetylene opacities in the K-band are pretty low, so we don't get good constraints on those. And we do get a bounded constraint on the water dissociation pressure, which is great. The issue is that when we take this posterior and calculate, all right, well, what is the C to O posterior, we get this sort of bimodal behavior where there's this peak at very low C to O and a peak at very high C to O. And that low C to O ratio peak is driven by a higher oxygen abundance primarily. And that happens at very deep water dissociation. So if the water dissociation is deep, higher water abundances are allowed because then they're dissociating and the water feature strength is comparable. So to try and disentangle what's going on here, we then compared with an equilibrium model. So in this plot, I have the retrieved abundance profiles for water, CO, and OH. In dashed dot red, I have the equilibrium predictions for a C to O ratio 0.1 and slightly subsolar metallicity equilibrium model. And what we see, so the posterior draws here are only for cases where the C to O ratio is less than 0.4. And what you can see is that these low C to O ratio draws all have the water dissociating quite deep compared to the chemical equilibrium prediction, right? There's sort of a bit of a tail, but in general, there's kind of a 1.5 dex discrepancy between those. But if we look at the full posterior, now there's much better agreement. And the maximum likelihood and the median retrieve profiles are in pretty good agreement with a C to O ratio of 0.75 and a metallicity of plus 0.7 dex. So that suggests that in the case of Kelt 20b, either there is this equilibrium high C to O ratio, high metallicity atmosphere, or there's some mechanism to be dissociating water much deeper than we expect. And I believe the high C to O ratio, high metallicity is a bit more consistent with previous results for this target. So the sort of takeaways from this approach is that you can actually retrieve freely dissociation parameters, but in doing so, you introduce degeneracies between the abundance and the pressure parameters that you don't have otherwise. And that can then bias your C to O ratios. So we're thinking about sort of 2 ways to deal with this going forward. One is to use the equilibrium profiles for at least some species. Say the water and CO we treat in equilibrium, but then you could freely retrieve other trace species that are maybe photochemically produced. The other option is to just use a better prior. Don't use a uniform prior if you have a real expectation on where the water dissociation should be happening in your atmosphere, or penalize mixing profiles that are very out of chemical equilibrium. So moving on to Celt 9, this is the KPV-CIS diagram we get, and the detection is kind of weak here, and in particular it's weak compared to what we expect based on the data quality and the other detections that we have. It's peaking an SNR of maybe 5, but it's offset. There's a bunch of other crap in the KPV-CIS space. It's not great. But this could be explained if there's, say, CO dissociation happening, and the CO features are much weaker than we would expect them to be. Now, unfortunately, when we try and run retrievals on this, we're getting a flat posterior, which is nice in that you hope a crappy detection gives you a crappy constraint on the posterior and that your retrieval doesn't wander off and do something questionably physical, but it is unfortunate for understanding the atmosphere. Fortunately, we observed Celt 9 twice. We also got a full transit with 90 minutes pre and post-transit. And when we look at the out-of-transit emission spectrum, we do actually see a somewhat stronger peak, closer to 6, an SNR of 6, and consistent with the expected velocities. When we run retrievals on this, we get a non-inverted PT profile, we see water, and we see weak CO. And that's pushing us towards a low metallicity, low C/O composition. Want to emphasize that that's very preliminary, very work in progress. We had a bit of a similar fake out with WASP-33b a few years ago. So we are still trying to vet this. But it is interesting, and potentially, right, for these ultra-hot Jupiters where the day sides are dissociated, maybe the night sides are a better probe of the composition. And then there's the clouds, so maybe not. So stepping back and seeing the sort of full sample we have, our targets were observed either pre or post eclipse. We were trying to be as flexible with the scheduling as possible. And so that led to a mix of phases, which means that we're actually looking at slightly different parts of the planet. The post-eclipse observations, you're seeing the morning terminator coming into view, right? So you're looking at sort of the morning longitudes of the planet, whereas pre-eclipse, you're looking more towards the afternoon longitudes. And if we compare that with where we see evidence for water in the retrievals, it's a kind of perfect split. We see evidence for water in Celt 20b, TY 1518b, and WASP 33b, and upper limits on water in the other 3. So that's maybe some indication of longitudinal distribution of these molecules. It would be really great if we had both pre and post-eclipse observations for some of these planets so that we could actually verify that that's what's happening in an individual planet, which I will be asking our TAC about in the next proposal cycle. But this is consistent with some other results, right? For WASP-33b, there's a pre-eclipse OH detection and a non-detection in the post-eclipse data, which does suggest, right, that maybe water is dissociating in those afternoon longitudes, but is not dissociated in sort of the morning region of the planet. So the goal of this whole survey, this whole project, is to try and understand what is the underlying ratio of C/O and metallicity. And there's all sorts of theoretical predictions here, right? I've shown one from Khorshid et al. 2022, and in general, the expectation is that the C/O ratio and the metallicity are inversely correlated. So I can put our very preliminary, very sketchily, don't take these error bars too seriously, constraints from the ultra-hot Jupiters on here. And one of the issues here, right, is that if you don't have a water detection, and you're doing this entirely based on CO, you get a C/O ratio of 1. So that's not really that informative. But even for the targets where we do have water detections, for WASP-33b, Celt 20b, and TY 1518b, those are all preferring high C/O ratios. Celt 9b, the night side, is obviously quite different, and we're still in the early phases of trying to figure that out. So that's interesting that these C/O ratios are all running a little bit high. The metallicity, unfortunately, high-res metallicity constraints aren't great, so they're solar to 10 times solar, but hard to make a statistical claim based on that. If we now show the preliminary results from other targets in our survey, and these are all targets that are cool enough we don't expect to see thermal inversions, We do see a little bit more diversity. Some of these are high C-to-O ratio, a few are low C-to-O ratio, but the only one that seems to be consistent with this sort of theoretical model is HG189733b. So there does seem to be pretty substantial diversity in this hot Jupiter population. So some takeaways. It looks like some ultra-hot Jupiters might have high C-to-O ratio and high metallicity, but I think making that claim is very dependent on how you handle the dissociation, the model parameterization, so we need to figure that out. And there's maybe some hints that there's a little bit more diversity in other hot Jupiters, but we really need more targets to make that claim more definitive. So I will stop there and take questions. Thanks.
Mike Line talking about exoplanet atmospheres of Gemini South. Any extra questions you have for Luc, please use the Slack. I see that letter phone.
All right, I'd like to thank the SOC. I'm on the SOC, but I didn't rig it, for the opportunity to give this talk. A number of people are involved in this survey. Feel free to talk to them. The ones in yellow are here. But before I start talking about science, shameless plug, I think there were a lot of people who are looking for postdocs. If you are looking for a postdoc and want to live in the great state of Arizona, where it's nice 8 months out of the year, and if you want to experience what it's like to live on an ultra-hot Jupiter for 4 months out of the year, come talk to me. I can tell you about this 51 Pegasi B application process. So just to remind everybody, I don't need to go over this a lot, but there's a bunch of questions we want to ask about planets. and atmospheres are a way of probing some of the answers to these questions, and we need to measure their compositions and temperature profiles to try and link, perhaps futilely so, the atmospheric composition to their formation conditions, and then we want to understand how their temperatures change with latitude and longitude and altitude to understand the mechanics of planetary climate, and then this is all building towards what we all secretly want to do on the inside is find aliens. So why IGRINS on Gemini South? And I'm sorry if I didn't put your instrument up here. There's like a new instrument every day. So why IGRINS on Gemini South? If you do the simple scaling that takes into account all the things, you find that IGRINS is kind of pretty high up in terms of the SNR capability of detecting lines in exoplanets at high resolution. So this was motivation to look for CO, water, other things from the H to K bands. And so this planet is old and boring now, but we first observed WAS77AB, which is kind of a generic hot Jupiter, nothing particularly special about it, to see how well IGRINS performed. This was a few years ago, and we demonstrated that you can actually get pretty solid detections of the gases you would expect, water and CO, and furthermore, we demonstrated that you could get precise constraints on the carbon and oxygen abundances and the vertical thermal temperature structures, which are things we wanted to do to answer those questions that I pointed out earlier. And it was nice seeing Luke's talk beforehand showing that different pipelines can give the same answer on the same data set. So I think we're starting to, really figure this out and do it well. And then Peter Smith talked about this planet yesterday, so I won't talk more about it. But this was motivation to go look at a bunch of other planets ranging from cooler hot Jupiters to hot, ultra-hot Jupiters over a range of gravities and temperatures to try and understand trends in the composition and the climate, and then to pull out the elemental abundance ratios with the idea of observing in the emission geometries, so pre or post-eclipse, to pull out those vertical thermal structures. So here's just a quick summary of the detections that we have. I'll go into some science later, but for a lot of these, we have the pre and post eclipse. That's why you get these nice butterflies here. And so this just demonstrates that we're actually detecting the thermal emission features across the range of temperatures that we're talking about. So I'll go through some quick highlights. So this is a paper that Matthieu led a few years ago on the ultra-hot Jupiter WASP-18. And what is nice about the IGRINS wavelength range is that you can get water, OH, and CO all together. So it's great for studying these ultra-hot Jupiters because OH is the dissociation product of water, and so you can really capture all of the, or most of the carbon and oxygen inventory, and this is sort of direct evidence that the depleted water abundances are due to thermal dissociation, which is why you're seeing the OH. And then shortly thereafter, the nearest SOS through the JWST Early Release Science Program team observed WASP-18 with covering similar wavelength ranges as IGRINS, and then you can show that we actually get good agreement between space-based and ground-based, something Peter also showed yesterday. This is just another example demonstrating that the ground-based observations can keep up with and agree with JWST. So it's important to keep demonstrating that so the JWST people will believe us. Yeah, so they do our proposals. Some additional highlights, again, from Peter, and this paper is submitted, and also I think talked to Stefan Peltier about WASP-121 as well. But sometimes we forget that in the near infrared, there's actually atoms that have transitions there too. It's not just in the optical. So if you actually look at the refractory species, the atomics, we can actually get detections of these species in the ultra-hot Jupiters. And so why do we care about that? I should point out that this was first tried with CRIRES Plus with Ramkumar and Gibson last year, and so this kind of motivated us to look for iron and other atomics in the infrared. But why do we care about this? Well, we've all talked about C to O and metallicity enough already, but a few years ago, some folks talked about how we could use these refractory species relative to these volatile species, the oxygen abundance or the silicon, iron, whatever, to add an additional lever arm on planet formation models. Whether or not you believe any planet formation models and if the predictions are actually useful, it still nonetheless provides an additional lever arm for testing potentially where a planet formed within the disk. So a goal that is emerging over the past few years is to try and measure both the volatile species, water, CO, all that stuff, and then these refractory species to try and do just that. You'll see more tomorrow, a talk from Jorge Sanchez, another student in our group, talking about all the wonderful things that you can detect in everybody's favorite ultra-hot Jupiter, WASP 189, so we can get the water, OH, and CO along with a whole bunch of other atoms, and he'll talk about what that means for the volatile to refractory ratios, but also the magnesium to silicon ratio, which came up earlier this week about how you can use that. That's an important metric for understanding terrestrial planets and how they're built. So he'll talk about what kind of constraints on all of these different ratios we can get tomorrow. And then this is some work from a student with Matthieu, looking at for some of these refractory species in another hot Jupiter, Mascara 1, the same one observed by these guys. And again, we're able to detect both these volatile and refractory species, so we can leverage that to try and have a more distinguishing power on some of these planet formation models. It's just sort of a summary. Ultra-hot Jupiters are the gifts that keep on giving. You just keep shaking them or whacking them like a piñata, and more candy keeps falling out. By candy, I mean gases. So let's talk about climate a little bit, and by climate, I mean temperature structure. So this is a fun planet, WASP 19. And so if you run your standard 1D radiative convective equilibrium model that does not have non-LTE in it, because that is scary, and only like 3 people do that because they're insane. I don't know why. Just a joke. So if you do that and you assume LTE for everything, you get a planet that has a thermal inversion in it. And when you cross-correlate a model that is generated with that, if you have an inversion, you have the uppy lines, right? So you have emission features. You end up getting a hole in your cross-correlation blob plot, which means you get this. There we go. You got to do it that way. So you get an anti-correlation, and so you get a hole. And so that tells you that what is predicted is not the correct temperature gradient in the atmosphere. So if you fudge around a little bit to remove the optical absorber such that you don't have a heating source to produce a thermal inversion, you could actually flip the sign of that to get a positive detection, which is telling you that, okay, well, what physics would make me go from an inverted atmosphere to a non-inverted atmosphere? Well, I remove these opacities artificially, but the way you can get those to be removed in real life is to have some sort of cold trapping on the night side, where these species condense into clouds and they don't persist on the day side to absorb that UV optical radiation to create that heating source. So that's pretty exciting. So now things are going to get a little weird. So if we call this temperature profile that it has the thermal inversion, it's an upside down HoRSE, he's inverted. And then you have the one that's decreasing, where we care about, that's the right side up HoRSE. And if we tag all of the planets in our survey with an upside down HoRSE for inversions and a right side up HoRSE for not inverted, we can just kind of do it like a silly thing and just say which ones are inverted and which ones are not. So the dots up here represent the planets that are inverted, and the ones down here represent the ones that aren't inverted. And you're like, okay, well, it flippies somewhere around here. How does that compare to, I don't know what we would predict. So we take, again, our atmospheric models that predict the thermal structure, and we ask, we go, oh, this one's a right side up HoRSE, and this one's an upside down HoRSE. If we do that with these models, we can put these different curves on here. And so the labeling of these are just the different physics, or I'm going to call it the climate parameter. So full redistribution means that the energy that is being absorbed on the day side is fully redistributed around the planet, so the day and the night have the same temperature. And then we can play around with different kinds of climate parameters, like if you assume that only the day side hemisphere re-radiates all of the energy, and you just have a hot day side, you get one thing. And if you use this cold trapping where the refractories are condensing and not absorbing, you can put those different trends on there. So, in a kind of fudgy, hand-wavy, non-Bayesian way, that's fine, Bayesian is fudgy. You can maybe say that, like, oh, we're seeing this transition is probably consistent. It's a delayed onset of these thermal inversions, which may be telling us about this cold trapping mechanism. I'm going to steal the Luc plot. So if you plot up the metallicity in C to O, these are some preliminary results, but this is kind of exciting because I think we're finding a similar thing where the metallicities are like all over the place, but the C to O ratios appear to be high. And so this is, I don't think this is a retrieval bias or anything because we take into account all the dissociation blah blahs. You know, so maybe there's something there. We can start to address, you know, how does the enrichment in the planetary atmosphere change with planetary mass, and how does that compare with other objects? And then we can actually start to retrieve the thermal structures to try and back up that statement about where that inversion transition is occurring. This is just the thermal emission survey, but you'll see Lorenzo's talk, I think, tomorrow, and then you can go talk to Megan Mansfield here. She has a survey that just undid to observe planets in transmission. So we're trying to combine all this stuff to get a coherent picture for, you know, how these planets work. And here's just some preliminary results. Well, actually, these are both published, so that's not preliminary. From Megan's survey highlighting that, you know, we're able to detect these carbon and oxygen-bearing species in cooler planets. And, you know, you can talk to her for what kinds of things we can do. So just to quickly summarize, IGRINS is like really awesome. Yay, IGRINS 2 is going to be in the Northern Hemisphere. We're all going to compete. It's going to be great. We're all going to work together. It's going to be great. So we can get metallicities, carbon-oxygen ratios. We can do refractories in the infrared. There's a lot of science to be done. There's hope for ELT, probably not the US ELTs, because who knows if they're ever going to get built. But, you know, European ELT is good to go. And I'll leave this shameless plug up here. So thank you.
We now have our penultimate session of the morning, so I know this is the hardest bit of a conference before lunch, so you know, please find your energy sources. We will now have Romain Allart talking to us about the first slide from NIRPS.
Hello everyone, so my name is Romain Allart. I'm a postdoc fellow at the University of Montreal, and I would like to thank first the organizers for this second edition of the HoRSEs conference, and it's nice to see some familiar faces from the first edition in Nice, but also much newer faces at such a conference. So today I will present you results on behalf of the NIRPS consortium, and maybe you are not aware of what is NIRPS, so I will start by describing you what it is. So NIRPS is this spectrograph here, that you can see here, installed on the 3.6 ISO telescope, meter telescope at La Silla in Chile, that can be operated simultaneously to HARPS, which is in the visible, and you can also, and because nighttime is not enough, we are also using NIRPS to observe during daytime with the sun and to have a RV sequence of the sun. So NIRPS is a AO-assisted fiber-fed Echelle spectrograph covering the Y, J, and H band, which is already reaching a 1 meter per second precision in radial velocities and providing high spectral stability. And therefore we have a few systematics. We have two pipelines to reduce the data, and these two pipelines both produce telluric-corrected spectra, which seems to be quite a nightmare for a lot of you. So it's a good thing for us. And we have two instrumental modes, the high accuracy and the high efficiency mode, and we recommend to all of you to use the high efficiency mode, and we can discuss this further after the talk. So NIRPS was built by a consortium led by Switzerland and Canada, and with contributions from Spain, France, Brazil, and Portugal. In exchange of building the instrument and taking care of a timeshare of a 3.6 meter telescope of ESO, ESO granted us 725 nights of GTO over 5 years, which is one of the largest program worldwide for exoplanets. And we started operation last year, a bit more than a year ago, on April 1st. So it's very recent instruments, and time to collect data, to solve a few bugs here and there. It's quite nice that we already have a first result to show you now. So how do we split this 725 nights? We decided to do 3 different work packages with the same amount of time, so 225 nights for each of them. The first one aims at detecting exoplanets around M-Dwarf in the habitable zone to be imaged with ELT, and this is something led by Lucille Mignon and Xavier Delphos in Grenoble. The second work package is led by our 2 co-PIs, François Bouchin and René Doyon, and which aim to do like the classical test follow-up to characterize mass and density of planets transiting M-Dwarf. And the last work package we have is related to atmospheric characterization and orbital architecture, and the one I'm leading, and so why I'm here today. And we also have some remaining time that we are using to do other science, such as stellar metallicity, stellar activity, program led by Elisa Delgado Mena, and also we have a sun monitoring, as I showed you before, with Xavier Dumusc. So let's focus a bit more on the work package 3 and the atmospheric characterization. So first of all, I would like to thank all these people who are mostly young researchers and that are contributing a lot to this, to the analysis of all the data. And I highlighted here in green all the people that are present in the room and at HoRSEs. So please feel free to go discuss with them about NIRPS and to learn more about it. So what do we want to do? We want to answer a few questions, which are: what are the physical and chemical properties shaping atmospheres? What is the occurrence of mutual misalignment in multi-planet systems? And how we can combine atmospheric composition, escape, and orbital architecture to constrain exoplanet evolution and formation. To do this, we are observing planets in transit and in dayside to constrain the chemical abundances, the dynamic, the temperature, and also different chemical processes such as condensation or clouds. For all planets that you are observing in transit, we are also looking to the helium triplet to measure the atmospheric escape, and we can also access the orbital architecture through the Rossiter-McLaughlin effect. And so we want to combine all these aspects for a few carefully selected targets to have a very in-depth analysis of their properties. And these are targets that we are following up over 5 years. So with the aim to provide something like a ELT-like fidelity signal-to-noise spectra over 5 years. But we also want to do such analysis for a very broad diversity of exoplanets, from the ultra-Jupiters to the sub-Neptunes, and try to observe statistical constraints on their formation and evolution. For the first half of the GTO, we are therefore observing all these targets, which is about the 70 most promising targets from ultra-Jupiters to terrestrial planets. And this represents a bit less than 300 time-critical data sets scheduled over 2.5 years. And so now I'll show you a few first results we obtained, and I just want to highlight that we have 2 posters about NIRPS, about the helium triplet here at HoRSEs from Danny and Vignesh, and you also learn more about ultra Jupiters in the 2 coming talks by Valentina and Stefan just after mine and this afternoon. But one of the first results we obtained was obtained during the commissioning of the instrument, and which is about the detection of water vapor in the puffy hot Saturn WASP-127b that we heard a lot this week, in particular with the talk of Lisa Nordman with CRIRES+. And so in a single transit, we are able to obtain this detection of water with NIRPS, which is again on a 4-meter class telescope. And so this is something that we are preparing as part of the first light paper, and we are following this target is one of a few that we are following up over the 5 years to accumulate high fidelity, high signal-to-noise spectra. And you are currently have 3 transits that are shown combined here. And this is a work led by Frédéric Genet at Montreal. And you can start to see the temporal evolution of the signature appearing by accumulating more transits. And I just want to say that we are doing all this analysis with a Starship's code developed by Anne Boucher, and you can, which is fully available on GitHub, and you can access here. A second result that I would like to highlight quickly is the detection of volatile and refractory elements in the ultra-hot Jupiter of WASP-121b. So it's something similar to what Mike Line just showed you before. And this is a work led by Luc Bazinet, who is present here. And we detected the presence of water vapor, I1, and OH. And so by combining the abundance ratio of these different species, we can inform the place of formation of a planet. And so we want to do similar things for most of our exoplanets. And I could not finish this talk without speaking about the helium triplet. So 6 years ago at HoRSE in Nice, Lisa Nortman and I presented the first detection of helium triplet at high resolution. And so with NIRPS, we are continuing the same program. And we have, in a bit more than a year, we observed all these planets that you can see here, and I highlighted in green the planets for which we have detections, and in red for planets for which we have upper limits. And so with this, we'll be able to perform some statistical analysis on the atmospheric escape that will allow us to provide insight on the exoplanet evolution. And I will provide a better look into WASP-69b here, which was also detected by Lisa Nortman in 2018. And you can see here this clear detection of helium, which is about a 60 sigma detection, just if you are wondering. And you can see the evolution of the signature as a function of phase. And from there, we can derive, for example, a light curve that you can see here. And you can clearly identify post-transit absorption up to 50 minutes after the end of the transit. But because we have this high-quality data set by the combination of 3 transits, we can also do something quite nice that have not been done too much for the helium triplet, is to see how the helium signature is evolving with time in terms of position as function of wavelengths, or also the equivalent in velocity. And so we can identify 4 different phases. The first one, which is before ingress and during ingress, which is where the signature is redshifted and going to 0 velocity. The second phase, which is shown in green, is the first half of a transit where it is constant in velocity space. And then we can see that the helium signature is being blue shifted and extended at even more extended at higher velocities during the transit. And combining this velocity shifts with post-transit absorption, it means that we are clearly probing an extended atmosphere with escaping material into space in the form of cometary-like tail trailing the planet. And because I had some questions at Exoplanet 5, I produced also this plot, which is a comparison of the absorptions of the helium triplet with a different result in the literature. So I only considered high-resolution spectrograph, and you can see here the data for Carmenes, JANO in green, NIRSPEC in orange, and Spirou here, and NIRPS here. So I would say at first order we are quite consistent, but it's quite difficult to really search for variability in this, because we are not reporting excess absorption and uncertainty in the same way, which is also a problem for molecules. And because we have all these discrepancies, it's quite difficult to really understand what is variability or what is just different analysis tools. So it's something that we should try to converge on during this meeting and also in the next years. And so, yeah, the helium triplet can provide access to the upper atmosphere, dynamic and variability, but we can also do a bit more and try to model this helium signature using 3D model of the thermosphere and exosphere, like we are doing with Yann Carteret. And you can also discuss more about the modelization during the week. And you can see here that we are clearly probing, the best fit model proposes a clear cometary-like tail trailing the planet. So WASP-69b is this hot Saturn evaporating. And on top of it, we also reanalyzed the Rossiter-McLaughlin effect with Vincent Bourrier for this planet. And so what we found was we used the revolution Rossiter-McLaughlin technique, and which give us access to the stellar surface radial velocity, which says that the projected obliquity is aligned. However, when you combine this information with the stellar rotation of a star, you can access the true 3D spin orbit angle, which is slightly misaligned of 30 degrees. So basically, you have your star a bit tilted toward us. And so it means that WASP-69b is evolving on a misaligned orbit with a escaping material and is thus joining an increasing population of Neptunian worlds, such as JG456b, ATP11b, and so on, that are really experiencing something in their lifetime, producing some evolution in some related to their exoplanet evolution. So to conclude, I would first want to say that it's very important to stay close to the instrumental teams that develop the instruments, because they have access to all the knowledge of the details of what is going on in your instrument and also in the reduction. On the NIRP side, we are dedicating 225 nights of nights to see exoplanet atmospheres and orbital architecture to provide high fidelity, high signal spectra to search for variability and prepare for the ELT era. And we also want to propose population survey of composition, dynamic, escape, and orbital architecture to constrain the evolution and formation of exoplanets. So please stay tuned for more exciting NIRPS results in the coming months. And I will just finish on the last announcement that next year in Montreal we'll host Exoclimb 7. And so if you want to join us, feel free to come to discuss with Vignesh, Joost, or myself who are present at the conference this week. Thank you very much.
We will now hear from Valentina Valato, who will be talking to us about NIRPs as well.
All right, can you hear me? Fine. So good morning, everyone. This is Valentina Valato from the Observatoire de Genève, still practicing my French. Sorry about that. So today I have the pleasure to talk about how NIRPs unveils the ultra-hot Jupiter's atmospheres, and I would like to start from the title itself. So Romain, in the previous talk, already introduced the NIRPs mission to all of you, but I would just like recap a few key informations about. So NIRPs is anchored under the 3.6 meter telescope in La Silla, and it covers the range of waves from 0.9 micron up to 1.9 microns. So it's covering the YJH band, so we actually miss the K band in this case. The high resolution is guaranteed, and it was designed to observe simultaneously with the HARP spectrograph to gather the optical counterpart of the telescope. The most suitable target to look for atmospheric studies are the ultra-hot Jupiters, and today I will pick one of the most famous one, which is WASP-189b. So let's go. So WASP 189b is the guy you see in the corner of the planet radius insolation plot. It relies in a closing orbit, so it's very highly irradiated by the A-type host star. The radius and mass are fully consistent with Jupiter-sized planets, and since it's very highly irradiated, we were able to measure the dayside temperature looking at phase curves from Keck's mission, and we measured at dayside temperatures close to 3,000 Kelvin degrees, so it's pretty high. And the very high irradiated atmosphere leads to extreme atmospheric conditions and significant dynamics at play. To unveil the ultra-hot Jupiter's atmosphere, we decided to opt for the trendy cross-correlation transmission spectroscopy technique. So we started by cleaning the data, getting rid of the infamous tellurics in the infrared, which are pretty disturbing. And then we shift to the star rest frame to calculate the master out corrected spectrum. Then we move to the planet rest frame to build and calculate the transmission spectrum. The build transmission spectra are cross-correlated with synthetic spectra that we generate from the Scarlet framework. The cross-correlation involves the shifting of the template over a range of velocities, and the cross-correlation is calculated at each shift. And the goal is to get the cross-correlation calculated for each shift to understand and to get informations about the detection or non-detection of specific chemical species. It depends on the template we want to cross-correlate with. The cross-correlation process is also repeated over a range of KP and VC's values, and for each pair of KP and VC's combination, we calculate again the cross-correlation to get the so-called KP VC's diagrams. And when we have the peak on the cross-correlation, that means that we got actually a detection. So let's move to the result now. So we gathered a couple of transits with the ARP spectrograph together with NURBS, of course, from the GTO time that we got. And as you can see from this couple of transits, we get a nice about two level sigma detection of iron. So we decided to focus on iron so far. And that's consistent with previous results, especially published by Stangert and collaborators in 2022. But that's nothing really new, so far so good. The problem, and we were a bit puzzled about it, is that we didn't find any iron detection in the near infrared counterpart. So looking at NURBS data, what we got was basically a flat line. And we were a bit puzzled about it. So the immediate question was why, and we started questioning ourselves why we don't detect iron in the infrared part of WASP 189b. So we questioned if maybe we need more data, if the instrument is not sensitive enough maybe. But at the end, we came to the question that maybe there is something that is preventing us to detect iron in the neutral iron in the near infrared. And about that, let me tell you a story. So the H- opacity is not negligible at all in near infrared spectra, especially in hot gas giant exoplanets. That's what we know from literature. And the H-, this is how the H- behaves from the optical up to the near infrared part. So it contains two main contributions, the bound-free transition and the free-free transition. I just quick remind you what bound-free and free-free transitions means. We have a bound-free transition to form H- when we have a neutral hydrogen atom in the atmosphere, and we have a free electron running around the atmosphere, and the free electron collide with the hydrogen atom, and it remains fully captured, forming ions for hydrogen. And the free-free regime, quite the opposite, the free-free regimes, transitions to form H- are given by a free electron, always, and the neutral hydrogen atom. And the free electron interacts with the hydrogen atom but it's not remaining fully captured. So we have H minus formation by these two interactions. The yellow box is where the NURBS coverage falls, and as you can see, the NURBS coverage is mainly dominated by the bound-free transitions compared to the free ones. Just keep this in mind, and now let's move to how the iron template is behaving as a function of the temperature. So what you see is a cross-section as a function of wavelength of the iron model built by Scarlett that we want to cross-correlate with the real data. This is built at 4,000 Kelvin degrees, so very high temperature, but let's decrease the temperature, and let's decrease the temperature again. And it's pretty evident that the higher the temperature and the stronger the iron signal is. But we must keep in mind that with transmission spectroscopy, we prove the terminator regions of the atmosphere of the planet, which are colder compared to the dayside temperature. So we deal with less lines and weaker lines compared to the dayside template spectrum that we can generate. So now let's merge all the informations about the H minus opacity and the template sensitive to the temperature all together in one plot. So you see on the light purple the iron only, calculated at 3,000 Kelvin degree, but that's not really matter. What matters is that if we take into account the continuum level also, so the H minus plus the iron at the same time, we get the blue spectrum. The red box is where NURBS, that we have NURBS data. But if we consider the observed data, we most likely discard the red edge of the detector and of the spectrum because it's very, very noisy. We do the same, so we mask where the CCD gap in the detector happens, and at the same point, we have very strong telluric water bands, and even if we correct for tellurics, we still have some remnants and residuals from the correction because the water telluric bands in those regions, in this region, is very, very saturated. So also this point data will likely be discarded. So we remain with a few survivors to cross-correlate with. So we have our template spectrum with these a few lines we want to cross-correlate with, and the real data, so the observed data. And as you see, we just have a few survivors lines to cross-correlate with, compared to the optical part, where we have stronger lines, crowded regions, and less affected by tellurics. Last but not least, we also must take into account the continuum level given by the H minus contribution, which dumps and kills the contrast of spectral lines. So we have just a few survivors lines, and those lines, the strength of those lines is also killed by the H minus continuum. So we start understanding that detecting iron in the near infrared part is not so obvious as expected. So as casting out nines, we also run injection recovery tests in NURBS data. So on the left side, you see an injected iron detection when injecting iron, the iron model only in raw data. So we actually are able to retrieve and to get iron from NURBS data, but that's not consistent with the reality. So that's life. So indeed, if we inject iron plus H minus, the iron signal is fully cancelled out and is killed, and that's consistent with the result. So this means that the H minus contribution cannot be neglected, and we must take it into account. But we were not happy, so we also decided to run retrievals, and this is what we get from retrieval results. So you have the probability on the y-axis and the abundance ratio between H minus and iron. The vertical red dashed line is where we expect results from the retrieval, so the chemical equilibrium. And from the blue distribution, of the ratio of the abundances, we surmise that we have more H minus than predicted by chemical equilibrium. And this may be evidence that we might have more free electrons than expected in the atmosphere of the planet. And the free electrons, the main donors of the free electrons to form H minus are given by the ionized metals, like also iron. And I would stop here with the lesson learned. So we have HARPS detection. We have a NURBS non-detection of iron. The temperature is playing a role, decreasing the strength of the line of the template spectrum we cross-correlate with, but also the H minus bound-free continuum absorption prevents us to detect higher neutral iron in the near infrared part of the spectrum. So maybe we need more electrons than we have more electrons than expected, and for that we want to check the far infrared part where we have the free transitions that are more deal with the electron density. So yeah, I'm done. Thank you so much. I'm happy to take any questions.
specifically within the yellow lines that you will see behind, so that you are recorded well, okay? And so without further ado, let me present you Thea Hoot, who is going to talk about the characterization of the atmosphere of a planet we all love, WASP-76b, with Piro data.
Thank you. Thank you very much. So basically what I'm going to present to you is mainly what I published earlier this year in my paper. So about, like, I'll mainly focus actually my talk on the dynamics part, but I will hopefully get enough time at the end to talk a bit about the CR ratio, which everyone loves to look at. And in particular, to connect to what I'm currently working on, which is to combine data sets, so either low with high resolution or high resolution near infrared with high resolution optical. So hopefully I'll get enough time at the end to talk a bit about that, but I'm not entirely sure. Anyway, so just to give a bit of context at least to the work that I'm doing. So this is part of the work that I've done is part of the atmospherics program, for which we do have a logo, and I think there's you might have seen it in the past. Something that you will not have probably seen in the past is that we actually also have a little mascot that's been on my blackboard for the last year. He does not have a name, so do not hesitate. If you've got any ideas, send them to me. And so this atmospherics program basically has united a team of mainly France-based researchers. The numbers are maybe not completely up to date. I'm not entirely sure. There's, depending on if I look at the Slack or the email address, there's different people. But overall, we do have, like, at least as part of the consortium, we do have 4 papers that have been accepted and published. 2 that are mainly focused more on the pipeline that we've developed that I'll talk about just afterwards. And so my one on WASP-76b and another one by a PhD in Paris, Adrien Masson, who focuses more on looking at helium with Spiri data. So within this consortium, we've developed an analysis pipeline to both clean and analyze the data. It's been mainly optimized at the moment for Spiri data, but can be very, very easily adapted for other instruments. I have used it on Marinix data. My supervisor, Florian, has used it on IGRINS data, I think, from what I remember. It can be very easily adapted. It can also be adapted to mission. The one on GitHub is mainly optimized for transmission, but it can be easily adapted for emission as well. And if ever you have any trouble, just contact someone from, like, either me or my supervisor, and we'll help you out. So I just wanted to say for the models that we mainly use are the ones that are made with petit retrans, that then we have a rotation, a broadening process to broaden the spectra to take into account rotation and instrumental broadening in particular. But if you want to use other models, you can use other models as well. Something I wasn't initially going to talk about or mention were the different steps of the data reduction, and I'm not actually going to go into very much more detail other than just saying, like, these are the steps of the reduction part of the pipeline. The reason why I wanted to just show this is because yesterday's talks about properly taking into account stellar effects using stellar spectra kind of motivated me to point out that at this stage of our pipeline, we do actually have an option where you can use synthetic stellar spectra to correct for the Rosetta-McLaughlin and center-to-limb variations. So if you have the synthetic spectra, you can just very easily use them. You should be able to very easily use them in this pipeline, in our pipeline. Now, another part of the context, just wanted to bring, like, for anyone who isn't fully aware of Spiri or, like, might have forgotten, I think someone did talk about it on Monday. It's a high-resolution near-infrared spectrograph that is located in Hawaii with a resolution of about 70,000 and has a continuous coverage from about 0.95 to 2.5 microns. And the good thing about this instrument is it's got very good accuracy in measuring the radial velocity. So it's very good instruments for looking at dynamics in particular. So WAS76b, I'm not going to spend too much time on it because I feel like everyone knows already a lot about it. In particular, the thing that was mainly interesting for us to look at that was to see if we could find the asymmetry that this planet is most known for in infrared data. So like, do we find in the near infrared data an asymmetry signal like has been put forward for iron and other optical absorbers, like those that were shown in Stéphane Pelletier's paper last year. So for this, I first looked at what I could detect in the data, so we managed to find water and CO, and what I found from my detections is that we definitely seem to have a signal that was dominated by the water signal present in the atmosphere. I want to mention that now because I will mention it again later on to do with the investigation into this asymmetric signal. So then it was like, so can we see for the CO and the water those absorption signals? So I am not claiming at all that I can see an absorption trail for the CO. I am just saying that if we were to see it, then the straight line is what corresponds to the KP and V-cis trail in here, that we see here. That's so the maximum correlation that I got here, the KP and the V-cis, that is what corresponds to the straight line. And the kinked line is what corresponds to the Ehrenreich signal for iron. So we cannot see the trail for CO, but from comparing those two lines, it does seem that it is the second part of the trail, the second part of the orbit that dominates the signal of CO. So that would maybe indicate that it's the trailing limb that is dominating the signal for the CO that we can see. For water, we can sort of see something, which if you maybe squint your eyes a bit, might look like a kink signal. I don't know. But what we did manage to do with the H2O signal, is, which I'll talk about later, is actually phase resolve the two halves of the transit. So so what can we learn exactly from looking with the H2O and or what could we expect maybe from the H2O and the CO signal? So actually seeing the trailing limb dominating the CO signal didn't really surprise me very much when I compared to Joost Owanye's plots for these plots of his from his 2023 paper. Seeing as CO and iron both absorb more in the dayside, so maybe because we're looking at the same, maybe probing similar or the same areas, it could be normal that we have the same sort of asymmetry. But for water, we are not, or do not expect to probe the same. We expect to more probe the night side, which is why I then tried to see if could phase resolve each half the transit. And I compared these to his models, and what this seemed to indicate was that it was more the optically thick clouds sort of model that seemed to correspond more to this water signal. Although, coming back to what I said beforehand about my signal being dominated by water, it didn't seem to correspond to the weakness of the H2O signal put forward by his models. So what I kind of thought that might infer is that either the clouds aren't as high altitude, or maybe they're more on the morning side. Which is, so I modified one of his equatorial plane plots from 2021 to sort of try and represent what I seem to could possibly infer as to the structure might look like, sort of, with clouds more on the day side, morning side than on the evening side, and this difference in scale height linked to temperature. And what I found is that definitely, my results definitely were consistent with other what others had inferred. So in Stéphane Pelletier's paper, he put forward from his results that it was the temperature asymmetry and or unevenly distributed clouds, which was consistent with what I found from my CO and H2O results. And then a month or two after I put my paper in archive, there was this KPIC paper that came out, for which there's a poster, I think. There is a poster in the poster room that puts forward clouds on the eastern terminator of WST76b, so the morning limb of the WST76b, which is completely consistent with what I seem to put forward, like my sort of very vague representation of WST76b, so I was very, very happy with that. So now so that was the dynamics, like asymmetry study. So maybe it might look like that. If any GCM modelers can come up with something like that so we can check it out, I'd be very happy to try and see. So I just do actually have a tiny bit more time than I thought I'd have to just very quickly go on the CO ratio. So I managed to measure abundances for water CO, but I could not measure for OH, HCN, or C2H2, but I did manage to find upper limits. And those abundance ratio limits estimations actually, so here led to me estimating a CO ratio that was significantly supersolar. And that's what I found was actually that is the 1 sigma area bar definitely kept it within that supersolar. But if you start going towards 2 sigma or even 3 sigma, it's actually not constrained at all. So I absolutely refuse from my results to say anything about formation. Definitely please do not ask me about that. But what my abundance estimates, at least, and upper abundance limits put forward were, they were found to be in agreement with those by Megan Mansfield with IGRINS data that was published a couple of months after mine. So I was very happy to see that everything seems to be consistent, which is brilliant, really reassuring. So basically, the reason why these error bars are so high on my data is mainly due to this fact that we don't actually have very good constraints on the CO abundance. In particular, we basically can't even exclude the ratio. So here I've just represented the distribution I got from my retrieval over what the corresponding CO ratios would be, and the lines represent what I had with my metallicity proxy, but I prefer to not mention that because the error bars on that are even worse than on the CO ratio. So yeah, I like to put that stuff back. I don't like really talking too much in detail about that things. I wanted to still, though, talk a bit about my work on the CO ratio because of the fact that I am currently working on combining data from different instruments. I realized that I wouldn't have very much time at this stage to actually show the results, so I'm just going to show sort of summary of what I seem to find, which is that combining high and low resolution did provide better constraints on the clouds and on the rotation speed, but did not help me to improve the CO ratio. For combining near infrared and optical data, I did manage to get actually much better constraint on metallicity by using the FE over H test as a proxy rather than the C plus O over H, which for the volatile metallicity. But I found that the degeneracy between the abundances and the clouds completely, the error bars were, again, really big and definitely needs improvement, but this is all very preliminary work that didn't last 6 months, considering that the last 3 months I've been writing my manuscript. So it's something that I haven't actually worked on for, it's current in between brackets, basically. So overall, definitely seemed to find from my work that WST76b temperature asymmetry with maybe morning-side clouds, but I definitely need better constraints on the CO abundance to get improved constraints on the CO ratio. At this stage, I would like to remind, because I don't think I insisted on it enough at the beginning, all of my results were obtained with using only one transit, one spirit-acquired transit. So obviously, maybe including more data could help improve the constraints. And something else that I felt like I could not mention is the phase curve observation that me and Joost Varnier got for WST76b, the phase curve observation with using James Webb. And so obviously that will probably help to improve everything as well. So very sorry about galloping through my talk. But please check out my paper if you want more details, or come and talk with me. And please do not hesitate to check out the atmospherics pipeline as well. Thank you very much.
It's Stefan.
It's Stefan.
Yeah. Your turn will come. All right, so now we welcome Stéphane Pelletier, who is going to talk about the presence or absence of titanium in another hot Jupiter. So Stéphane.
Titanium. It's the 22nd element of the periodic table. It's like the 20th most abundant element in the universe. Not something we care so much or think about too much in our everyday lives. It's useful to make some jewelry, some tools, airplanes. So some people care about it, I guess, but why do we care about titanium as exoplanet people? Because of titanium oxide. It's known to be a very strong optical absorber. So here I'm showing the cross-section on the y-axis as a function of wavelength, and I'm comparing titanium oxide to water, which you can see water has a very weak opacity dropping off to the optical range, which is why we see stars in the night sky. But titanium oxide has like stupidly strong opacity at optical wavelengths, and that's where a lot of stars emit their light. So titanium oxide is a very potent optical absorber. What that means is that TiO can be a very strong driver of thermal inversions, shown here in the plot by Gandhi et al., 2019. On the y-axis, you see the pressure, and on the x-axis is temperature. And here are shown different self-consistent temperature-pressure profiles for some hot Jupiter, where you would have, in one case, no TiO, and you would have a non-inverted temperature pressure profile. And then if you just crank up your TiO abundance, all of a sudden you'll have an inverted temperature profile. And you can think of this as just the starlight can reach deeper in the atmosphere without TiO, but with TiO, it absorbs it in the upper atmosphere, heats it up, and causes this thermal inversion. And this is not just some theoretical concept. We measure these things in hot Jupiter atmospheres. So here I'm showing some boring hot Jupiter at 1700 Kelvin, and then some less boring ultra-hot Jupiter. And you can clearly see that there's this transition from non-inverted temperature structure to strongly inverted temperature structure on the ultra-hots. So it's not some theoretical concept. And you could speculate, oh, one has TIO and one does not. So this is why TIO has been such a huge interest in the exoplanet community going back decades. And honestly, what a mess. You have these, it's like high resolution detections of TIO, and then like same group analyzing their same data with a better line list. Oh, detection is weaker and at a different place now. And this one's my personal favorite. You had Meredith did a really nice work clearly ruling out any evidence of TIO and VO in the atmosphere of WASP-21. Non-detection of TIO and VO in the atmosphere of WASP-21. Next paper, detection of TIO and VO in the atmosphere of WASP-21. Like, what's going on, people? But TIO is hard, and some of the difficulties come with the line list issues. It's like, it's gotten better, it's good, but it's not perfect, and it's kind of uncomfortable. We're not sure how good it is or how far we are from perfection. It's definitely good for some things. But there's this, we can bypass this issue, and this was actually kind of a concept introduced or proposed by Jens, is instead of looking for TIO, let's just look for TI, because in these hot Jupiter atmospheres or ultra-hots, you could have TI and TIO at the same time, and you can kind of probe for TIO using TI as a proxy. So here's an example on some ultra-hot Jupiter where you see all of the metal lines, but no TI. So where is it? And here what was proposed is that actually all of the metals that you see, these are refractory elements, but the difference with TI is it's actually an ultra-refractory element. I didn't make this term up, that's actually a thing. But TI, it just loves to condense. So you're at a temperature where you see all of these refractories, but potentially titanium would still be cold trapped, and which is why we don't see it. And you might think, oh, maybe we just don't see it because we're not sensitive to TI. Maybe TI doesn't have as many lines, but as I and others have shown, here I'm showing a plot on the y-axis is kind of the enrichment levels of different elements normalized to iron with respect to solar. So on the bottom is depleted, and on above is enriched. And what you see is most elements are, more or less consistent with solar, and then you reach, to some extent, these are organized as a function of their condensation temperature. You see these ultra-refractories are just depleted, not just by a bit, but like up to orders of magnitude. So it really seems like this cold trap completely depletes them. But cold traps can be broken. So here I'm showing just back to the cross correlation. This is WASP-76, where we see iron and we do not see any TI species. But you just crank up the temperature, go to another ultra-hot Jupiter that's even hotter. All of a sudden you see TI species and all their glory. TIO, TI, TI+. So it really seems like you can break this cold trap and unleash all of the TI species. Now, I had some fun, and now I'm just going to show you the hot Jupiter population. So it's just radius as a function of temperature. And here, circle size, I just made this plot for a proposal, so that's why circle size is like favorability, but you can ignore that. I'm just going to plot places where we've detected iron, like unambiguously. And you can see that, like, really, iron is ubiquitous in all of these ultra-hot Jupiter atmospheres, and less so in the normal hot Jupiter atmospheres. And as we say, probably because it's condensed, and then when it's hot enough, then you see the iron. And so when I think of an ultra-hot Jupiter, I think of something with iron in its atmosphere and a strong inversion. Now, what happens if I put titanium, neutral TI? So all of these have iron, but now looking at TI, you can actually see that there's some where we can strongly rule out titanium, and others where now we can see titanium. So you really see that the hottest ultra-hot Jupiters all have titanium species, and the cooler ultra-hot Jupiters do not have titanium. So you kind of have this titanium transition zone where presumably maybe that's where we break the titanium cold trap. And so one of the questions I've been asking myself is, this breaking of the titanium cold trap, is this kind of a, bam, you either have 0 titanium and then you have 100% titanium, or is this just some kind of gradual process here where you slowly release the titanium and then eventually you have enough that we can see it? So we targeted this planet WASP-189 with NIRPs with the goal to kind of measure this titanium to iron ratio and see if is all of the titanium there or are we still missing some. So we observed WASP-189 with NIRPs, and then the nice thing with NIRPs is we get HARPs for free. Cool. And we observed WASP-189 in secondary eclipse, well, or the day side of WASP-79, so when it's kind of behind the star and we see its hot day side. And then we ran a standard cross-correlation method, and you can clearly see here signals from iron and neutral iron and neutral titanium. And the day sides are the emission signals. Yeah, they're emission signals, so that means the temperature structure is thermally inverted, as is expected. But we can move beyond from cross-correlation detections and run atmospheric retrievals and actually measure the relative abundances of iron and titanium on the day side of WASP-189. And what we find here is from the results of a free retrieval. So I parameterize the abundance of iron as fixed with altitude and titanium, and then you can have TiO and the ions in there also. And when you add everything together, it seems that like there's less titanium than the ratio of titanium to iron is below what you expect from both the sun and the host star. So there seems to be some titanium missing. But this is a free retrieval. Like, come on, dude. This is an ultra-hot Jupiter. There's like ionization for like dissociation of things. There's probably other trace species. So we tried to kind of account for that as best we could by running also a chemical equilibrium retrieval, where now you can take into account of other trace species, ionization and whatnot, because one of the issues is that actually titanium ionizes more easily than iron. Now running this chemical equilibrium retrieval, you can see that we can actually explain part of the missing titanium from including all of these chemistry aspects, but there still seems to be some missing titanium, as far as I can tell anyways. So, where's the missing titanium? And I just want to highlight that this is not like just me, but there's some other works that also have been leading to kind of underabundant titanium ratios relative to iron. So when we actually retrieve the temperature structure, here I'm showing, the dayside retrieved temperature of WASP-189, and you can notice that it's hotter than where we expect titanium to condense, like everywhere throughout the dayside. So I'll just say a word of caution, and now we can put our theorist's hat on. So be warned, because I'm an observer by trade. But potentially what this could mean is that actually a vertical cold trap of TiO is unlikely, because everywhere on the day side, it should always be in gas phase. But potentially, you could still have the night side be cold enough for some titanium to condense, rain out of the atmosphere, and then it could still circulate back to the day side. But we see some on the day side, so potentially it's just you don't see all of it, and it's still somewhere in the atmosphere, just not in the upper atmosphere in gas phase. So either it could be partially cold trapped, or there's not enough vertical mixing to bring it all back up. But again, this is where we're in theory land, where I'm out of my comfort zone. So if you have any ideas of how we could potentially explain this, come talk to me. Thank you for the hat. I'll go back to the observer world now. So to conclude, we observed WASP-189 that it's dayside with NIRPs and HARPs. I forgot to mention, but NIRPs is actually what's driving the signals because you have a better flux contrast, even though you have less lines than HARPs. We detected iron and Ti. When we measured the titanium to iron ratio, as best as I can tell, there seems to be some titanium missing, and partially this could be that this breaking of the cold trap is actually, it's not either you don't have any titanium or you have all of it. Maybe you just kind of gradually release the titanium, as a gradual process. But if that doesn't make sense, come tell me. I'm not sure, but thank you.
Thank you, Stefan. Questions? Okay, Jens, I Okay, so now we are welcoming Clara Sousa Silva, who is going to talk about the challenges, I think, of spectroscopy for planetary atmospheres. So the floor is yours.
Thank you. Hi, everyone. When I thought about giving this talk, I was just going to list all the things that I think you're all doing wrong, and then I realized it would be a major downer, and so there's going to be a very short summary of some of the problems I see or worry about, and some of the kind of promising paths forward. So that it's not too depressing. So, you care about spectra, I care about spectra. We'll start with the most obvious part. You want to detect any molecules in space, you need their spectra. You need to know what each one of them looks like. But that's often hard. So hard that it takes us to the first problem, which is we don't have enough spectra. So, as a reasonable example, my old group at MIT, I think I'm going to have to not do this. Yeah. My old group at MIT estimated that in a potentially habitable atmosphere, there should be up to 16,367 different molecular species. Now, you can be skeptical about it, and it's true, a lot of these molecules would contribute very, very little to their atmosphere, but even molecules that are present in very small quantities could be really crucial providers of context for molecules that are abundant, that you do care about. And we don't yet know which are important and which are not, so in the meantime, we should probably care about them all. The problem is, can we detect them all? We cannot. We can detect less than 4% of them. And by detecting, I mean generously detecting. We have some spectra for them. Fortunately, there are promising developments. Since the lack of spectra is a problem, my promise is we can just make more. Now, you can measure the spectra, but that requires a lot of lab work. It is often dangerous, sometimes illegal conditions. A lot of health and safety guidelines will not let you measure a lot of these molecules at the right temperatures and pressures. And so alternatively, but more usually alongside experimental work, you can make spectra with computers, which is what I do. For example, take phosphine. We know quite a lot of a spectrum, but that's only because I spent my entire PhD doing it. And it was really hard, and phosphine is only one of these molecules. I would love to repeat this for the thousands of molecules we're missing, but this multiplies very poorly. Because one person working on one molecule using very fancy computers still took me 4 years of my life and a conservative estimate of sweat and tears. So if I was going to tackle the remaining thousands of molecules at this rate, I estimate it would take me a little over 60,000 years. So we need some shortcuts. There are many very clever people doing very ungrateful work on this aspect. For example, I have some collaborators at the University of New South Wales, and recently a student-led approximate quantum chemistry calculation set got spectra that was pretty good for basically every phosphorus molecule you might care about. Now, this worked better for some of the molecules at some of the wavelengths, at some of the temperatures, but it's a really good start. And they recently upgraded their approach and simulated almost 3,000 of the sponge or schnapps molecules, just to fundamental frequencies with really impressive accuracy. In the meantime, I am lazy and don't always want to do the really, really complicated computer simulations, and so I created Rascal, Rapid Approximate Spectral Calculations for All, using mostly organic chemistry to generate instantaneously, basically, approximate spectra for any arbitrary molecule, specifically just the relative intensities and band center positions. It does this okay, so this is dimethyl sulfide, really cool molecule on Earth produced by algae. And this is how well Rascal can kind of simulate the experimental spectrum. It's not perfect by any means, but it's a start. And it's specifically a start that can be used to figure out how sensitive your models are to different molecules in different wavelength regions with different intensities, so we can figure out where to put our energy into really high-resolution computational simulations and really dangerous and expensive experimental measurements. But what it's also useful for is to learn of the traps in assigning molecules to spectral features. So, for example, take hydrogen cyanide, HCN. Its infrared spectrum can be completely explained by this cute little CH group, basically through its multiple vibrational motions, which I can tell you about if you like. You can explain all of the main features, which means if you detect any of these features, you can be like, oh, maybe I detected hydrogen cyanide. Or acetylene, because it has the same functional group within it and the same strong features in the same place for the same reason. And any guesses here, how many other gas phase molecules have this CH group triple bonded to something? A lot. 890 by Rascal's calculation. Fortunately, sometimes a molecule's strongest feature is not its most distinguishable feature. So one of the things that Rascal can tell you is, yeah, 1-butene and propene, same strongest features as HCN and acetylene for the same reason, but it has other features that maybe you want to use to tell them apart. But basically, any molecular detection that doesn't take this sort of degeneracy into consideration will be vulnerable to false positives, false negatives, misassignments. And to kind of show you what it looks like when you think of things like methane, hydrocarbons have very similar problems. They all have carbons and hydrogens bonding in very similar ways. So here in green is methane, not too hard to detect, particularly in high resolution, but all the other hydrocarbons, so isoprene in red as an example, and in gray, all the hydrocarbons, have very many similar features, and so you may need particularly high resolution to be able to distinguish between these. And specifically, if your models only have some of these hydrocarbons, it's not unlikely that you can fit your data to whatever hydrocarbons you give it, and it doesn't mean you found them. So that brings me to the next problem, which is, if your models are going to work, you need to trust the data we give you. And very often, the spectra is not good enough. The spectra that does exist for those 4% of molecules I gave you some hope for is rarely good. And what I mean by good is it needs to be accurate. Thank you, Hassan, for showing this plot before. Accurate means theoretical measurements, theoretical calculations and experimental measurements agree with each other, and the frequencies and intensities are correct. But you think, what else can you possibly need beyond accuracy? It's accurate, you should go home. But good spectra is not just accurate, it is comprehensive. It covers all the regions that you need. Here, you're looking at hydrogen peroxide. In blue is what most models were using for the longest time, because that's what we thought hydrogen peroxide looked like. It wasn't until theoretical simulations showed that it is spectrally active in a much wider range of wavelengths. Not just hydrogen peroxide, this is formaldehyde, same problem. And I could have an entire talk just listing all the stuff that would be wrong if you use the experimental data. But I'll give you a methane example, because methane has been quite well measured. There's some really accurate experimental line lists with a really impressive coverage. So right here you see in white the observational spectra for a methane-rich brown dwarf, and using an experimental spectrum with 350,000 really accurately measured features across the whole frequency range, you could model it quite well. But you actually needed 10 billion features, theoretically calculated in this time, to make it work. And actually, this wasn't even a fully comprehensive, accurate line list. This has now been updated twice to be a much larger methane line list that you should be using, also through XML. But theoretical simulations and laboratory measurements are not at odds with each other. They're synergetic. And modern laboratory measurements are very accurate, but they're mostly restricted by the instrumental limitations and also the pressure and temperature you made that measurement, and it's very hard to extrapolate correctly from it. Theoretical calculations are very good at that extrapolation, but they're often a lot less accurate. And so combining the two is how we can really improve data. So these were energy level networks that were actually developed by a bunch of children as part of a program I worked on for acetylene, and now we're doing the same thing for phosphine. And so both of these line lists were heavily improved by this collaboration between experiment and theory. This to say that to solve the problem of not good enough spectra, we can just make better spectra. And sometimes that needs to be a real priority. Like Hassan gave some great examples on Monday, and like you just saw with methane. But sometimes it isn't a priority. For example, collaborators of mine led by Prajwal Nirala, who at the time was a PhD student, looked at the aero budget of JWST observations and found that the choice of opacity sources, as well as broadening and following parameters, was really consequential in many planetary targets, but sometimes it didn't matter too much. So characterizations of large, hot, and metallic exoplanets like WASP-39b in transmission were mostly independent of a lot of opacity choices. So, you know, well done to you all for not having to worry about the opacity sources you use for this, but is it well done? Because remember that really exciting sign of photochemistry in the form of SO2? Seems great, and SO2, definitely a strong candidate, I would say, for this, but so are many dozens of other molecules, like a lot of molecular candidates. But there's hope. Remember that CH group I highlighted earlier? Well, molecules with CH, but also NH, have strong features there, but they also have a strong feature here, which isn't there, so that tells us we can narrow that huge candidate list to actually just this many, which includes SO2, so maybe well done. This sort of like big data approach to spectroscopy is finally providing us and you with the tools to fully contend with the ambiguity and the degeneracy of your molecular assignments. But we're trying to also do other things. Another collaboration I'm working with is looking to systematically identify and rectify weaknesses in rocky planet atmospheric models, specifically photochemistry, and then retrievals, depending on what you use. So one of the things we've done is seen the water spectra in the UV, where it's really, really weak. And so a lot of inputs for water in the UV just cut it off. Because it's so weak, you're never going to detect it, and it probably doesn't matter. Except it does. My own theoretical simulations built on the tireless work of experimental measurements that are noisy kind of showed that there's probably water absorption, very weak water absorption, well beyond what we thought. And although it's so weak you would never use it to detect water, it is photochemically consequential. Specifically, when we updated our water spectra, we changed the quantity of OH, which changed the quantity of a bunch of other molecules. So even the really, really weak spectra that you think does not matter can easily matter. So we did it again with CO2. And we found that actually in this case, changing the CO2 spectra to include these really weak opacities made some differences in specific scenarios, but most of them were immune to this update. So sometimes you should care, sometimes you don't have to care. The problem is, it's not just spectra. If you remember the Venus observation of potentially phosphine and its controversy, one of the sources of controversy was the lack of broadening coefficients that meant we couldn't really guess what the abundances or the altitude were. And in fact, I'm on teams that both find and do not find phosphine on Venus, but even the teams that agree that the signal is real but think it's SO2 can do that because with a very well characterized line, but a single characterized line, you'll still never get an unambiguous detection. And on that topic, even if phosphine is present in the clouds of Venus, explaining its presence relies on understanding its production and destruction network and associated reaction rates, and it will come as no surprise to you, we don't have those, or any spectra for the intermediary products. So best of luck doing false positive scenarios for phosphine or anything else. And there's much more. Prajwal also looked at all the other sources of uncertainty they could have in models, and as you can see, there are many. I promise you here there is an easy solution because it is almost impossible to do this work theoretically, so you just have to fund some measurements. And money is hard to get, but it is at least a simple solution. But there's an associated problem to this, which is there are no accepted community standards for any of this, what to use, when, and with what consequences. Which is why, fortunately, as Essen mentioned, we have Maestro coming online, an international collaboration led by Nicole Lewis and Natasha Battaglia. And that is, the goal is to tell you what data you should use, what its limitations are, and specifically who to cite, because this is ungrateful work. But for example, it can tell you things like, if you care about MGO, TIO, and VO, you're probably using the wrong line list because there's an updated one that hasn't yet been published, but you can find if you have some friends at Exomol. And if you're using water, even if you're patting yourself on the back because you're using the Pockezatel line list, that is still wrong. We have an update, there's Marvelize. So the point is, talk to us. You don't have to figure this out on your own. But the problem here is it's a lot of work, and we're running out of time. We're going to get all of these fancy things. Some of them we have already. We're hoping to get this really fancy thing. And if you wait for your fancy data to show up before you ask us for better data, we won't have time to do it. It takes years to do this stuff. And so my next promise, the only solution to this problem, is we need more folks of every relevant field and career stages. So here are my students, some of whom were high schoolers when they started doing this work, and they're working on fixing all the molecules for everyone. And on that note, I spent about 4 months of my time in Porto, and I have a PhD position open right by that bridge on the left. Starting in the fall or winter, I'm flexible, so let me know. And to stick to the theme, here's my kid.
Thanks. All right, so now we welcome Yuri Damasceno, who is going to talk about the origin of a species he detected with espresso in, is it an ultra-hot Jupiter as well? Yeah, okay, excellent. The floor is yours.
Right. Thank you very much. So, hi, I'm Yuri. I'm a soon-to-be PhD student at the Universidade do Porto. And I'm just here to show you some of the recent results we got on the transmission spectroscopy of WASP-178b observed with espresso. And this is a work that has already been accepted for publication, was supervised by Julia Seidel, Nuno Santos, and Bibiana Prinot, who's also here. And so to start, David Cont already did a really good introduction of the planet, so thanks for that. But just to quickly recap, WASP-178b is a bloated ultra-hot Jupiter, quite similar to some of your favorites, such as WASP-189b, 76b, 121b. But what actually makes it different and sort of special is its host star. So it's actually orbiting a type A1 star, which is the second hottest star known to host an exoplanet only after Kelt 9. And so for some context now, we also got, we had the bonus of using some simultaneous photometry observations with EulerCam, which allowed us to get some updated parameters for the stellar parameters, planetary, and also orbital. Now, regarding previous studies, the atmosphere of WASP-178b has already been observed and studied in the near ultraviolet using instruments aboard the Hubble Space Telescope in the Lothringer et al. Paper. And actually at the same time as our study, David also analyzed it in the near infrared using CRIRES+. And both of these actually already found some very intriguing results. So there's a huge near ultraviolet absorption that was observed with Hubble, and also the detection of water and carbon monoxide with some very broad signatures in the emission spectrum. And so our transmission spectroscopy results sort of come to complete this bridge with visible band observations to provide some complementary information, which is really nice to have for an ultra-hot Jupiter. And so what I want to show you now are some of the main results or highlights that we found from this work, which actually start way before the transmission spectrum. So more of a fun fact, we started by finding 3 pairs of sodium lines in the stellar spectrum, equally spaced from the stellar line, which is shown by the vertical dashed line. And we expect these to be actually caused from the interstellar medium, or more specifically 3 separate clouds that are moving at different radial velocities, which we found to be a pretty curious finding. But of course that had to end because we had to remove one of the lines due to low signal to noise, but it was still fun while it lasted. But now moving on to the actual transmission spectroscopy results. So we were able to detect a series of species, starting with hydrogen via the H-alpha and H-beta lines, which are shown here, where the thin yellow line represents the instrumental broadening for espresso, which is around 2 kilometers per second, and the green dot dashed line represents the escape velocity in function of height. We were also able to detect sodium via the D doublet, which is shown here co-added in velocity space, and also we tentatively detected magnesium with one of the B triplet lines. Then we also tried to use the cross-correlation method to detect iron, both in the atomic and ionized state, which are here shown, and once again we tentatively detected magnesium on this atmosphere. And so these are basically the main results for our paper, so the detection of all these species, but what can we actually extrapolate from these to know more about the atmosphere? And so one way to look at this is in function of height, or in descending order of height, starting with the hydrogen lines, which probe the uppermost layer of the atmosphere. And what we see immediately for these is that the broadening is quite high. So for example, the H-alpha line has a full width at maximum of around 40 kilometers per second. And if we compare this to the escape velocity, we could see that if the fastest moving particles are high up enough in the atmosphere, say 30% of the radius of the planet, it is possible for these to actually escape the atmosphere. So there is a possibility of atmospheric loss at the very top layers of the atmosphere. And next up, there's sodium, which probes below hydrogen in the atmosphere, but still mid to upper atmosphere. And here we see a big decrease in the broadening and also no shift at all. And now, although this value is still above the instrumental broadening and the thermal broadening, which is also around 2 kilometers per second, it's quite below the value that we would expect from other similar ultra-hot Jupiters. And so for comparison, I have this table here which shows some full width half maximum values for sodium lines detected in similar ultra-hot Jupiters, and on the bottom is the value that we obtain. And we can see that even if we use our widest sodium line, it's still way below what we would expect from other ultra-hot Jupiters. So this kind of raises the question whether wide sodium absorption features are a common or a global property of ultra-hot Jupiters, or if there are other factors that are contributing significantly to this. And there is another very interesting result in Langeveld et al., which shows that there is a certain consistency in blue-shifted sodium absorption, which is also something that we don't see in WASP 178b. Now, if we relate both of these things to atmospheric dynamics, for example, this could indicate very vaguely that perhaps in this layer of the atmosphere, there's surprisingly weak dynamics when compared to other planets in the same population and of the same type. And so to top it off with the lower layer of the atmosphere, which is probed by IGRIN and our tentative magnesium detection, we see that here there's an increase in the width of these lines and also significant blue shift. And so still in the same train of thought as before, this could eventually be a vague indication of atmospheric dynamics appearing stronger in the lower layers of the atmosphere. And this would actually be in agreement with some of the previous results done for this target. So for example, the Pagano et al. Paper found an efficient energy recirculation, which was related to the presence of zonal winds, so from the hot day side over to the cooler night side. And also the Cont et al. Paper found broadened water and carbon monoxide features, which were associated with rotational winds in the lower layers of the atmosphere. And both of these could also be used to explain the blue shift and to explain the broadening that we see for these lower layer lines. So now if we combine all of this extrapolation, what we get is actually a quite peculiar image of the atmosphere of this planet. So we see quite the dynamics happening in the upper layer and also in the bottom layer of the atmosphere. But somewhere around the mid to upper layer probed by sodium, it seems to be suspiciously quiet when compared to other planets. This is very intriguing to see. And I also want to show you some very interesting plots that we made for the relative light curves for each of the detected lines, and where we basically take the average flux around each line, and we divide it by the adjacent continuum. And we get these panels here, where the top two ones show the results we get for each night individually, and the bottom one is a joint plot. So what we can notice here is that there is what seems to be an asymmetry between the two nights that were observed with espresso, such that in the first night, the sodium absorption, the absorption in general is deeper during the first half of transit, but we see the exact opposite on the second night. And now this could, of course, be caused by some instrumental error. It could be caused by stellar contamination. But it could also perhaps be an actual asymmetry that's present in the planet's atmosphere. And there have been a couple of interesting talks about asymmetries in planets' atmospheres, including ultra-hot Jupiters. So I would be very glad to hear if anyone has thoughts or ideas regarding this, these results. And so just to quickly wrap up the conclusions, we were able to detect the hydrogen, sodium, and tentatively magnesium using narrowband transmission spectroscopy, and also IGRIN, both in the atomic and ionized form with cross-correlation. And these signatures seem to tell us that there might be a stratification when it comes to dynamics in the atmosphere with height, with what seems to be an unusually calm or undynamic mid to upper layer of the atmosphere probed by sodium. But one of the main takeaways, besides, of course, the transmission spectroscopy, is that there is a new ultra-hot Jupiter on the market now with some very interesting properties, both stellar and planetary, and that have already shown some promising and intriguing results on previous research. So it's definitely worth giving this planet more an in-depth look. Such so that we're also planning on submitting an observing proposal for a follow-up study with espresso as well. So we can hopefully clear up some of the uncertainties that were left open with this one and get a better grasp of what's actually happening in the atmosphere. So I'll now be happy to take any questions you might have, and thank you very much.
Hello. Yeah. Okay. Okay. So now we welcome Danny Munzer, who is going to tell us about a not so boring hot Jupiter. Danny.
Hey everyone. I'm Danny. I'm a last year PhD student at the University of Geneva, and today I'm going to present to you the transmission spectrum of HG189 733b around the sodium doublet with espresso. And here we go. So HG189, we don't really need to present it anymore. It's the closest transiting hot Jupiter. It's been discovered 20 years ago. There's plenty of papers on it and it's mostly because it orbits an active bright host star, a K2 host star. And so we've observed it with for 2 transits with espresso, and so with the capability of the VLT to get so much photons, we get really high signal-to-noise ratio on those observations, which were really good. So good that in the RVs we can see the RM really well, and even in that RM we can see a spot crossing in the second transit that we also see in simultaneous photometry with Euler. So the idea is that we took this data and we used our in-house workflow Antares to correct for this data. Antares is a set of modules that can be activated or deactivated to do a lot of things. I used it for the data preparation and cleaning and such. And also for espresso, what's interesting is that it corrects for the what we call the wiggles. So it's this behavior pattern that you see that goes crazy at the helium, crazier than even all the other espresso data sets, and it corrects for them really robustly. And so yeah, we can just go ahead and see what our transmission spectrum looks like. So around the sodium, it looks like this. Oh, by the way, I use absorption going up. If you're used to down, this will be up. Okay, so upwards, we see the RM on the atomic lines very clearly. Okay, but what the heck is going on in the sodium? If I zoom in, you see that the RM is still the dominant effect, but there's these 2 wings that appear. Are they planetary, or what is it? Is it the double jet? Well, let's figure it out. So here I showed a 2D map of the stacked lines of the 2 transits. So I co-added both sodium lines, and we can see, okay, this seems to be the planetary signature. It follows the sodium line quite well at the planetary rest frame, quite blue shifted, but we don't see this other red wing. Where is it? I don't know, but we see the Rossiter like clearly well. Okay, so now what do we need to do? We want to mitigate this stuff. This is really bad. Okay, so to do so, we redid the Rossiter-McLaughlin analysis using RM revolutions, and with this we can get the surface RVs for each of our exposures, which is great, and we rederive all the parameters that we know of HG189. It's a line system, and we find those velocities that are similar to what we have had in the literature before. And so we start trying to correct for this RM. Okay, the most naive part would be masking the stellar track. So we don't like this. Boom, disappear. And so if we take the average of all this, we have this blue wing that is left. But the red wing has disappeared. So is this red wing lower speed than this, or is it blended in the star? Is it from the star? We don't know. But of course, we're not going to keep this because we lose a ton of signal to noise. So let's jump to the next one. So we usually for your usual transmission spectrum, you use Fin over Fout, so the master the spectra in transit over the master out of transit. We go a step backwards in the simplification of this formula, and we want to use the local spectra. To do so, we use the surface RVs that we got earlier, and we use the master route. We suppose that the master route is a sufficiently good proxy for that, and we shift it to the local velocity. Okay, what do we get here is this. Okay, this is weird, because is it an insufficient correction? Probably yes, because here in the nickel line we see that there's still something remaining, and we know from previous studies that there's a remnant even if we do that. But the behavior of both lines is very weird. One looks like there's still a Rossiter, or maybe a double jet again, and this one looks just like it's in large absorption with the wide absorption, with a wide full width, I would say. Okay, so let's go further. Let's try to model all those planet-occulted line distortions. So to do so, we generate the spectral stellar grid of local spectra using turbo spectrum that match the master out. We input those spectra into evaporating exoplanets to simulate this transit within an atmosphere. And here at the top you have the non-corrected data with the model superimposed with it, and this is what we get. This looks vaguely like the second one, which was derived from observations, and this is synthetic, okay? So what is going on? Is it insufficient? But now we've corrected the nickel line properly. We need to do so for the sodium as well. So okay, from what we, okay, now if I, with this correction, I do the 2D map again with the lines co-added and with the with just the line co-added and both transits, and we clearly see this blue planetary wing, but there's nothing at the ingress, and the rest of the absorption, it seems, is just following the stellar track. So what the heck? Okay, here's a summary of those corrections. But what's most interesting is if we look at the different steps during the transit, we clearly see that maybe it's undercorrected or something. But we clearly see in the regions where there should not be those line distortions, we see the absorption in the blue wing that we don't see afterwards in the red wing. Okay, so our conclusion is really that the blue wing is planetary and the red wing comes from the star. All right, but we can go a step further. The idea is to just do the combined feat of the atmosphere and those effects on the absorption spectrum, and what we want to do is to reproduce the shape of the local and the disintegrated lines. If we do so, we'll find the same transmission, the same absorption spectrum, and we can just explore a whole plethora of atmospheric winds and stellar parameters. So we do so using still Eve. We had to add the chromospheric sodium to our 1D and non-LTE models to actually match the sodium, the core of the line of the sodium, and with those parameters we find the atmosphere of the sodium behavior around HG189 all the way to the Roche-Loeb radius. So if we take this profile into account, we get here you have the signature in the D2 line and the D1 line, and we fit both together, the atmosphere and the planet-occulted line distortions. We get this black line for no atmosphere, and if we really think this is stellar and we just look at the blue part, we are compatible with an atmosphere of day to night sign winds between 8 to 10 kilometers per second. But yeah, as Gloria Kanoki mentioned yesterday, this is an undercorrection, which on the other side is overcorrection, which is what we had on HG209 458B. So we should actually go 3D later on to see if this is not coming from that specifically. But the real question is, all this time we've used the master route as a proxy, but is it actually good enough? And if we look at H alpha, this is what we have. So this is the transmission spectra during both transits of H alpha, and you see that there's a blue tail and a red tail post-transit, and so this means that the sodium at the core of the line just decreases really a lot during the transit, and we see this on the sodium as well. So if I divide the pre-transit master by the post-transit master, we get that the core of the line has varied quite a lot, up to between 1 and 2% on both transit, and we see this in this final 2D map, this blue tail here and the red one here. And so basically, there's something going on in the star, of course, because it's an active star, but basically all of this behavior is not really well understood what is going on the Doppler stellar track of the star, basically. All right, but this could be detrendable using Antares, or if maybe we could add a time-varying parameter for the chromospheric sodium in Eve, and if it decreases over time, maybe we could actually fit a new master to get this correctly, but this is work in progress. Here are the takeaways of what I've just told you about. There is sodium in HG189, but the espresso data, it seems to favor fast day to nighttide winds, and actually now we see that the corrections that we've been making all this time for the ORM maybe are not trivial when we go to this high signal to noise and this high resolution. So we need to go deeper on that, and well, using better stellar models, either going 3D and understanding what's with what we add in the chromosphere. The stellar activity definitely plays a role here for HG189, and there's still some interrogations about the interpretation, because basically all the papers on the sodium of HG189 kind of contradict each other. This one adds something else, like with those very fast winds and still absorption and not that same absorption. And yeah, that's it. Thank you very much.
All right, and so for the final talk of this first part of the session, we are welcoming Jennifer Glover, who is going to show us what we can do with spectroscopy for reflected light.
Thanks. Hi, my name is Jennifer Glover, and I'm a first-year master's student at McGill University with Nick Cohen, and today I wanted to talk a little bit about detecting reflected light at high resolution. So Sophia gave us a good introduction to reflected light yesterday, but I wanted to start by quickly recapping. By reflected light, we mean starlight reflected from the surface or atmosphere of a planet. And as a first-order approximation, the planet's reflected light spectrum should be a faint Doppler-shifted copy of the host star spectrum. This approximation is commonly known as the planet having a gray albedo. So why is it important to detect reflected light, especially at high resolution? Reflected light is of course related to the planetary albedo, but it can also give us insight into the temperature and detailed energy balance of a planet. It can give us insight into cloud properties. For example, things such as the scattering phase function of cloud particles can be learned through reflected light. On some planets, reflected light may give us insight into surface structure. For example, ocean glint may be visible in reflected light. And finally, reflected light can give us insight into atmosphere composition and biosignatures. So near-term searches for biosignatures will rely on detecting reflected light at high resolution in optical and near infrared. So despite reflected light being very important, it's also very challenging to detect. So this equation is the reflected light contrast, that is the expected flux from the planet to the flux from the star. And it's related to the geometric albedo of the planet, the radius of the planet, and the semi-major axis of the planet modulated by a phase function. Since semi-major axis is a somewhat accessible parameter to learn about a planet, when we conduct reflected light searches, we're really interested in learning about the albedo and perhaps the radius of the planet. So if we want to pick the best possible target for detecting reflected light, we want to maximize this contrast ratio, which would mean choosing planets which are large and on close-in orbits. This sounds a lot like hot Jupiters. So on this plot, there's geometric albedo on the y-axis and the radius of the planet over semi-major axis squared on the x-axis, and contours of the full phase contrast, which is the quantity in brackets, are shown in blue. For context, I've plotted solar system objects and labeled them with their first unique initials. An average solar system planet has a reflected light contrast on the order of 10 to the negative 10, which is extremely small, and an average hot Jupiter, which are in the lower right corner in red, have a somewhat larger reflected light contrast on the order of 10 to the negative 5. So this means that even though hot Jupiters tend to have really low albedos on the order of 10%, they still are the best targets that we have for reflected light searches. So I want to highlight a few studies that have been done searching for reflected light at high resolution. Martin's 2015 was the first study to claim a greater than 3 sigma detection of reflected light at high resolution. And this study was followed by that of Borat and Deschatelet in 2018, who also claim a significant detection. The remainder of the published studies on this list only claim upper limits on the planetary albedo and radius, which has called into question the detections of Martin in 2015 and Borat and Deschatelet in 2018. Nonetheless, these studies do show that it's possible to detect contrast ratios on the order of 10 to the negative 5 or greater with current instrumentation. This means that it's likely just possible to detect reflected light from ideal planets such as hot Jupiters at this moment. I want to point out that future instrumentation, such as Andes on the ELT, will aim to detect contrast ratios of potentially habitable planets and solar system analogs on the order of 10 to the negative 5 and greater. Okay, so I want to take a moment to talk about why those particular 4-5 planets were chosen as the targets for the previous searches for reflected light. And this is entirely due to trying to maximize the signal to noise of the planetary reflected light. So we expect the signal to noise should be proportional to the reflected light contrast and then the signal to noise from the star. This means that we want to maximize the reflected light contrast, so choosing planets on close-in orbits, and also maximize the signal to noise from the star, which means choosing bright targets. In this plot of stellar magnitude and semi-major axis, this means choosing planets from the top left corner. Of these planets in the corner, they tend to be non-transiting planets around bright stars, and 51 Peg-b is the only planet that currently has a significant detection, even though this is a very contested detection. So the goal of our project is to detect reflected light from the hot Jupiter 51 Peg-b with approved observations from the optical high-resolution spectrograph Maroon X at Gemini North. These observations are planned very, very imminently for late July of 2024. So let's all please hope for good weather. So the previous studies searching for reflected light from 51 PEG have relied on the first three relied on the same set of observations taken with HARPS, and the next two studies augmented this original data set with more observations from HARPS North and HARPS respectively. So this means that our proposed work will be the first attempt to use an 8-meter class telescope to detect reflected light from 51 PEG-B, and it will also be the first attempt to use Maroon X to detect reflected light from any exoplanet at high resolution. What we want to use to detect reflected light is high-resolution cross-correlation spectroscopy, which we've talked a lot about this week, and the technique for reflected light very closely resembles similar techniques for emission and transmission studies that we've talked about. Importantly, it's not restricted to transiting planets, which means we can access brighter host stars. This technique relies on the fact that high-resolution spectrographs are capable of resolving Doppler shifts in the planet spectrum, which means we can disentangle the planet signal from the star signal. And importantly, especially for reflected light, where the signals are very small, it can boost the planet signal according to the square root of the number of lines in the spectrum. So for a solar-type star in the optical, this can be a couple orders of magnitude increase in our significance of detection. So I wanted to sort of go through what a search for reflected light with this method might look like, following the method of Martin's 2015. So begin, you take a series of spectra as the planet moves through superior conjunction, and these spectra will contain signals from the star and some from the planet. You first start by obtaining a template spectrum. Since the spectrum of reflected light from the planet should be primarily a copy of the host star spectrum, a good choice for template might be a model spectrum based on the spectral type of the star, or it might be an average of your observed spectra. In the next step, you can cross-correlate each of your observed spectra with this template to obtain a series of cross-correlation functions which contain a signal from the star and a signal from the planet. In the next step, we want to isolate the signal from the planet from the signal from the star. So what you can do is obtain a cross-correlation function which represents just the star and divide your observed cross-correlation functions by this template. What you should obtain is a series of residuals containing noise and then the planet signal at various rate of velocities. In the final step, you can leverage known orbital parameters of the planetary system to shift and combine those residuals into the planet rest frame to boost your significance of detection. So what we did to test this is synthetic injection recovery tests. We injected simulated planet signals into a spectrum modeling 51 PEG and recovered them with the technique on the previous slide. We chose to use a Phoenix stellar model to represent the spectrum of 51 PEG and convolved it to the appropriate resolutions and broadenings. We then injected this with Gaussian noise to match our proposed observations with Maroon X. Our tests show that it's possible to significantly detect reflected light, so greater than 3 sigma detection from 51 PEG-B, if it has a full phase contrast of 1.2 times 10 to the negative 5 or greater, which would correspond to an average hot Jupiter. So, in conclusion, detecting reflected light at high resolution is important but challenging, and high-resolution cross-correlation spectroscopy techniques have the potential to produce significant detections of reflected light from 51 PEG and other planets with current instrumentation. This is good because we have upcoming observations of 51 PEG with Maroon X. In the future, we want to investigate non-gray albedo scenarios and alternate techniques with the eventual goal of moving towards something that looks like retrievals for reflected light. For the exoplanet community at large, future work also includes eagerly awaiting the next generation of instruments and observatories which should be more than capable of detecting reflected light from a variety of planets. Thank you so much for listening, and please reach out if you want to talk more about reflected light or potentially collaborate. Thank you so much.
And so for this last 2 talks of today, we are first going to hear Gabriel Marleau talk to us about a survey of helium in exoplanets.
Great, it's really great to be here, excited to talk to you all today. I think this is the first time I've talked at a conference about this work, but we've been running this survey since 2019 when I first got to UT, so it's exciting to talk about it. Okay, so let's jump in with one slide of motivation for this survey. I feel like I can only motivate like one science thing in a 12-minute talk, so let's motivate this. So this is the mass radius diagram of all known planets. Anything bigger than about 1 Jupiter radii, right, 1 to 2 Jupiter radii, all of those are inflated giant planets, right, by some mechanism. But we have a hole in our inflated planets right up here, right? There are very few inflated kind of sub-Saturn mass objects. And so, oh, I'm standing out of my box. I have to stand in the box. Okay. So there's very few sub-Saturn mass objects, right? So we can postulate reasons why that might be, right? Once they get inflated, they're low density, low gravity. Perhaps atmospheric escape is really affecting these objects. Okay, that's our postulation. That's our hypothesis, right? This would classically be observed at like UV wavelengths, right? Something like Lyman alpha or metal lines. UV telescopes are very oversubscribed. And so the game for this all changed, of course, back a number of years ago in 2018, where we saw atmospheric escape using this helium feature for the first time. This was first seen at low spectral resolution from space with HST by a nice paper by Jessica Spake. But of course, this is not best done from HST. This is best done from the ground with high-resolution spectroscopy. And so we started to see a flurry of observations like this one by Allart et al. In 2019 from the Carmenes spectrograph, where we're now able to resolve this helium triplet. This is a metastable transition of helium, and we're able to get all of this information from this kind of infrared spectroscopy. So I was just starting at UT Austin at the time, and I was like, hey, well, they have this little 3.5 meter telescope. Everything's bigger in Texas, right? We have this 10 meter class telescope, the Hobby Eberly telescope, and it had a new, at the time, instrument on it called the Habitable Zone Planet Finder Spectrograph, designed for precision radial velocity work, but we can use it too for our nefarious purposes for atmosphere escape characterization. And so we started this program. Okay. So, observing with the HET. So, as you know, a planet transits maybe for like 1 hour every 3 days or so for a typical kind of hot Jupiter, hot Saturn-sized planet. Our beautiful 10-meter class telescope does not point up and down. It only points side to side. And so we have a logistical problem here where we have to figure out when all of the giant planets in the sky transit, and then figure out when they're passing through the height that my telescope is pointed at so that I can observe them. When I can observe them, we can move our secondary mirror a little bit, so we can observe them for about an hour, give or take, based on the position on the sky. So we design these observations not like a traditional transit observation where you observe for just, 6 hours or something like that and your transit's kind of in the middle, but we have this program where we observe our transit track, that kind of sets when we're going, and then we observe as many tracks as we can on either side of it. And so that's typically 2 days before, the day before, transit track day, the day after, and the day after that. So we end up with this time series data with this spectrograph. Okay, so the spectrograph is great. It's like a broad J-band infrared spectrograph. We use just one Echelle order out of that whole range. It's a resolution of about 55,000. So it's really kind of optimal for this kind of work. Okay, so our first target was WASP-69. Nortman et al. Had just published that this had this beautiful detection, and so we said, okay, let's make sure this plan works, because we were doing this kind of atypical plan. And so you can see here, this line here, this is our helium triplet, and you can see the black line is during transit. So this helium line is always present in the star, right, but it's deeper during the planet's transit. That's exactly what we see here, so, well, that's good. So cool, it works. And it's our result for this is kind of broadly consistent with the results from the prior Carmenes observations. And so we were satisfied that this was working and launched into a larger program. And so we're covering a range of different kinds of planets in this program. Here they are shown in one set of dimensions. And so this is gravity here. You might imagine that low gravity planets would be more susceptible to atmospheric escape. We also imagined that the stellar effective temperature might be important here. There's an idea that if you have planets around K stars, that lights up the helium by kind of raising it up into that metastable state where you can see this line, but not so much UV flux that you ionize the helium, and then you don't get this transition. So we designed this program to have a variety of K-dwarfs, but also some warmer targets so we could kind of test that theory. We could also, we kind of constructed this survey that also had a range of different planet sizes in it. 10-meter class telescope, right? We can try to push to smaller planets. And also, you can't see it in this graph, but we also had some young planets in here too, so we could see if this was also kind of a function of age. Okay, now I'm going to introduce you to my two favorite planets coming out of this survey, HATP67b and HATP32b. I'll introduce them together because they have pretty similar properties to each other. So both of these are very inflated. They're both around 2 Jupiter radii. HATP67 has an upper limit of its mass of 0.59, putting it kind of in the Saturn-sub-Saturn range. And HATP32, 0.68, it's kind of between Jupiter and Saturn in its mass. They're both right around the same equilibrium temperature, 1800, 1900 Kelvin, and they're both around F stars. And so we weren't expecting, based on our contemplations about how the stellar UV flux would affect the helium feature, we weren't necessarily expecting to get our strongest detections here. We can put these on our mass radius diagram just to kind of contextualize them in theory land too. I'm a theorist, by the way, so anyway. So we have this mass radius diagram here. Now we've added model tracks on here that show you how inflated you might expect a planet to be based on our understanding of the inflation mechanism for hot Jupiters. And so you can see they're sitting on the edge of this space, kind of right, hanging on by a thread on the edge. Okay, here's our data for HATP67. So we have the transit data from TESS, which was also looking at these planets at the time, kind of in the background, so you can picture the passage of time, years going by. And we have all of our observations for HPF are here as these blue lines. So you can see that we're observing during transits and then kind of bracketing it on either side of these. Okay, let's zoom into what the spectra look like here. Okay, so these are our spectra. So you can see that the after transit data is these green lines here. Before transit is blue, and the transit data is orange. You can notice a few things right away. So on average, the transit data has the deepest helium feature here. So this helium line is the one we're thinking about. The after transit data always has the smallest feature, and then the before transit is somewhere in between. The other thing that occurred to me when I was putting this slideshow together, I was like, look at these dates. April 2020, we were operating our telescope fully through. We never had to shut down. Super proud of our team at HET, and then also super proud of my team at UT because I had a baby in May 2020, and so my team was like doing all of this, running all of it. It was great. Okay, anyway, let's now calculate the equivalent width. So the equivalent width, we can phase this all up. And when we calculate the equivalent width, we see a really interesting shape to this that had not been seen before. So we see that this is the whole orbit of the planet, right? Minus 0.5 to 0.5 is the whole orbit with transit in the middle here. We can see that we have this kind of gradual slope up, and then it kind of cuts off right at the end of transit where this dashed line is here, and then it's kind of flat afterwards. And so what this tells us is that there's this preceding trail in front of our planet, and then it kind of cuts sharply off after the transit itself. We can do something really naive in theory land, having measured the depth of our helium feature during transit, and model what kind of escape you would need, assuming a 1D model for this clearly 3D thing. But you can nonetheless do this calculation to kind of guesstimate how much atmospheric escape that you might be seeing here. And you get something like 100 Earth masses per gigayear. And so for something that's just a few hundred Earth masses big, right? You're seeing a planet that's kind of catastrophically evaporating at this time. Okay, we can do something similar for our very similar planet, Happy 32. And this is our equivalent width. So if you look at the top here, equivalent width, we plotted it both ways, both with absorption up and down, so that it doesn't matter whether you're like an up absorption or down absorption person. Okay, so what you can see here is kind of flat, 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 and then starts to go up prior to the transit itself. During transit, you have the peak equivalent width, and then it comes down. It comes down more gradually than our HAT-P 67 observations did, but nonetheless has kind of similar morphology here. For this one, we actually did some 3D modeling to try and figure out what was going on here. And so here's a 3D model made by Morgan MacLeod at the CFA. And so what you're getting here, right, is escape that's coming off of your planet. It's kind of sheared along the orbit of the planet. The way to get this leading tail, but without a trailing tail behind it, to like 0th order, is that you have escape from the day side of the planet. When you have that preferential day side escape from the planet, assuming your stellar wind isn't so strong that it's kind of blowing that material immediately back outwards, then you can end up with kind of shear that then goes inwards towards the star and precedes the planet itself. So that's our kind of basic picture here. One thing I will just note in passing is that this picture seems like it's physically distinct from the trailing tails that we see in like the WASP-69 observations that I showed you first, or in planets like GJ3470 that also seem to have these trailing tails. If we go back to Theoryland for a sec and think about how our planets, what might be driving this kind of atmospheric escape, these are really nice models that kind of match the perimeter space we care about here really well. These are it's going to be a movie in a second, so get ready. So this includes XUV-driven mass loss and also includes the evolution of the planet itself as you're getting energy into the planet that's inflating the planet. Okay, so it includes both of those kind of physical mechanisms, radius inflation and XUV-driven escape. So you'll see the models here. So the models are all of these kind of points here. You'll see them evolve over time, starting at 0.001 gigayears. Okay, here they go. So you can see that they increase slightly in radius as you get energy injected into them, inflating them. Once they cross that line, they start to be dominated by that atmospheric escape, and then they kind of very rapidly, kind of catastrophically fall apart. Here, we'll play it one more time because it's really fun. Okay, there they go. Whee! We saw this came out right as we were doing this analysis. We were like, oh, hey, that's what's happening with our planet. Good, okay. So our data for the remaining targets can place limits on the helium escape. So we have these 4 detections. HAT-P 32 and HAT-P 67 are the ones I showed you. The stars mean that somebody else also detected them. So those are pretty robust. WASP-52 has a tentative detection by us and other teams. And then WASP-69, which I also showed you. And then we have upper limits on all of the remaining targets here. Okay, I'm going to advertise 2 more things in the next 30 seconds, okay? So first thing is I have a new paper out on what is like normally my day science job on modeling brown dwarf and kind of directly imaged planets. These are probably not at a high enough resolution for people in this room, but if you want me to post-process them at high resolution, tell me and it'll like bump it. For every person who says something to me, it'll like bump it up 1 notch on my to-do list. Okay, second ad. I had to have a horse. So this is how non-Americans picture Texas, as far as I can tell, having told people that I live in Texas over the last few years. I actually don't live in a place that looks like this, for better or worse. I actually live in like a big city of 1 million people. It's beautiful, it's green. Anyway, you care about this, some of you anyway, because I'm trying to hire a postdoc right now. I have some money that's actually gonna like disappear if I don't spend it. And so you should talk to me about that. At least one of you I've accosted one of you directly already. Plus there's like 51 PEG, Hubble, all of that for if you're on a longer time scale. So think about Texas. Okay, I'll put up my conclusions and take any questions. Thank you.